you start. My presentation today about how we develop Nanotechnologies for very interesting process. It's a transformation of tetrahydrogen by hydroxylic acid into acid. Production of adipic acid in the past and now realized using the integration of benzene with cyclohexene and after this oxidation up to cyclohexanol and cyclohexanol mixture and step-by-step oxidation using nitrous acid with homogeneous vanadium catalyst with formation adipic acid. Adipic acid used in industry for the preparation of different polymers, drugs, solvent, and other purposes. Obtaining of adipic acid is possible through biomethod and we use some ferments, but a lot of adipic acid started from cyclohexane. Last year, in scientific literature, published many articles about preparation of adipic acid from some biomass or product of transformation in biomass, for example, from cellulose. In this transformation, a K product is hydroxymethyl fluoride, which can transfer energy into 2,5-400 carboxylic acid and step by step transform it in adipic acid. More exactly, this mechanism included coordination of proton to tetrahydrofuran rings. Ring opening is formation of hydroxide and iodine group. And after this, step-by-step deleting of iodine group, first and second, at pressure of hydrogen using different heterogeneous catalysts. Main side product in this reaction is corresponding ester, which formed a reaction of 2-hydroxy adipic acid with some organic acid, which used as solvent for this reaction. Generally, in literature published different type of heterogeneous catalysts, which tried for such transformation. It's naphthalene, polymers with ensured SO3H groups. It's palladium doped silica. It's liquid crystals which consist from SO3H group and iodine groups. It's zeolites and palladium doped mixed titanium and molybdenum oxide or neoprene oxide. In all cases, high conversion and high selectivity can be reached only for platinum doped palladium or rhodium doped materials. We try to develop method of preparation heterogeneous materials, which will be cheapest and very accurate. For this, we tested two type materials. It's zeolite, the hydrogen for on bulk zeolites or hierarchical zeolites with different topology, morphology. For example, nanosphere, the nanosheets, nanorods, or nanosphere. And also, second type of materials is sulfated or phosphated titanium dioxide with different sulfur titanium or phosphorus titanium. Reaction was conducted in special upper flow, high pressure upper flow under hydrogen with control of pressure and temperature. First type of materials was with different morphology. As example, in the slides presented different zeolite materials with morphology of ultra-thin nanosheets. Such materials possess very high external surface and a high concentration of Bronsted as well as Lewis acid centers. For determination of concentration and strength of substance, we use a different method. For example, so named adsorption probe molecules such as pyridine, which can discriminate Bronsted and Lewis acid centers and determine concentration and evaluate strength of such acid centers. Despite of high concentration of acid center and very developed external surface, zeolite materials show moderate activity with maximum yield near the 25%. We believe that microporous zeolite is very small for such reaction and transformation of intermediate for carbonic acid in additive take place only in external surface, maybe with not so high concentration as necessary. Concentration of acid center is necessary. Second type of materials, it's titanium dioxide, which possesses ensured SO3H group, typical strong Bronsted acid centers. Such materials have another structure and show typical mesoporous structure, and it's conglomerate of small crystal organized in sunflower-like agglomerate. Such materials was prepared by our college in Nanomaterials, and in the series of samples, we try to change to titanium ratio for calculation of concentration and strength of acid centers. As we can see, with increasing of sulfur to titanium ratio, we with increasing of C to titanium ratio, we can see the concentration of acid center increased, and increasing of pKa, really it's increasing of the strength of acid center, and also increasing micropore volume and decreasing of external surface. As you can see from the curve of nitrogen absorption, in this series, we can see step-by-step transformation of mesoporous materials into typical microporous materials. Evaluation of the stability of such materials shows that all of the samples possess high concentration of Bronsted acid center and small concentration of Lewis acid centers. Testing of catalytic activity of such materials in this reaction in transformation of the into additive acid show that all of samples have good catalytic performance, but maximal activity showed samples with C to titanium, sulfur to titanium near 1. Increasing of such ratio, decreasing activity. Decreasing of such ratio also decreasing. After leaching test, this typical leaching test is next. After 2 hours of reaction, heterogeneous catalyst was separated by centrifugation, and reaction issue was relocated and reaction was continued up to typical 22 hours of reaction. You can see that after deletion of heterogeneous catalyst, conversion of intermediate current carboxylic acid not increasing, that shows that deletion of catalyst stopped at the first stage of reaction. But next stage continuing because we have increasing of very strong increasing of selectivity. For second, third, and other stage, not necessarily with the heterogeneous catalyst because this stage catalyzed by presence of iodine ion and pressure of hydrogen. Similarly, renewables powering of this catalyst in concentrated acidic acid in concentration acetic acid showed that we have not seen some decreasing of the so sulfated group in sulfated titanium oxide, a very strong anchorage to surface, and we have really situation with heterogeneous but not homogeneous catalyst. In attempt to find some correlation between properties and the performance of such materials, we try to find some correlation. You can see that no correlation between total acidity and the activity of, for example, concentration of sand or strength of sand. Similarly, no correlation with some surface area of water. When we calculated concentration of active sand, in this case, as I said, in external surface, using method which can be seen on this slide. So for both series, mesoporous materials and microporous materials, we can see very good correlation in concentration of the center and catalytic performance, conversion, selectivity, and yields. Similarly, series of phosphate materials, phosphated titanium oxide, can see similar dependence, but most active is catalyst with phosphorus to titanium ratio 1.5. So a different form of zeolite can catalyst can aid as catalyst for preparation for production of particular seed from different seed, but best catalysis in our case is very cheap materials. It's sulfate oxide, which again, gain total transformation.
Thank you very much. You're very interested in the presentation. I gave the questions. The first one is on information. The second question is about the regulation. Practical application of such materials.
The critical preparation of such samples is next. It's tetrabutoxide titanium, which mixed with sulfur acid. After hydrolysis deformation of air, such materials was hydrothermally at 115 degrees. And after this, careful washed by water up to neutral pH. Dry it, and after this, use it as catalyst. When we will calcinate these samples, the catalytic activity significantly decreases. We believe that sulfur provoke restriction of increasing of size of the nanoparticles and stabilize this structure and formate some very high estimate surface. And next, calcination of such samples provoke some decreasing of catalytic activity, but very careful washing of such sample and drying. Practically, we can obtain similar activity as for fresh samples. In what? Yes, what?
About the analysis, those the 100 is but in such in the share analyze transport of time. No, it's stabilize the structure. And yeah, correct. One question.
Good morning. Thank you for introducing the topic. I have one question. You talked about phosphate titanium side. Do you consider the composite with other phases, titanium state with other phases, for example, phosphate? Thank you.
Case for us need strong surface active samples. It can be sulfate group, it can be phosphate group, first with two or one OH group. And in both cases, strength of such acid center enough for propagate or this transformation. When we have some mixture of phase that can be questioned about stability or some solubility of different phases. In our catalyst, samples is very stable, and we can say that more some elimination was in solution. It's very principle.
Have any questions? Thank you very much. It's parents from Central National University is online.
Good morning, everyone. I hope you can hear me well and see my presentation. Yes, so
yes, everything is okay. We can see your presentation in full screen mode, so you can start.
Thank you. My name is Andriy Terets, and together with my colleague Timofey Nikolaenko, we are pleased to present our work entitled Parameterizing in Force Fields via Transfer Learning for Enhanced Nanomaterial Simulations. And let's begin. The design of the new molecules and the optimization of chemical synthesis rely heavily on the ability to accurately predict molecular energies from structural information, which is essential for material simulations. And in recent years, machine learning has become a powerful tool for this task. But a key challenge remains: the illusion of improved accuracy due to error compensation. The problem arises when the ML models directly approximate the total energy of the molecule rather than learning its physically meaningful components separately. As a result, these models may generalize poorly to the new molecular systems. And to address this issue, we combine principles from DFT with the representational power of graph neural networks. Our approach investigates a two-stage framework for molecular energy prediction. In the first stage, we generate physically motivated descriptors based on electronic density and kinetic energy which associated with individual atoms or atom pairs. And in the second stage, a separate neural network uses these descriptors to approximate the parameters of classical interatomic potential. According to the virial theorem, the average value of electronic kinetic energy operator equals to negative of the system total energy. And it can also be shown that this corresponds to the sum of the products between the kinetic energy matrix K and the electronic density matrix D. And this suggests that the neural network trained on the atomic and bond contributions represented in these matrices can form informative feature vectors or also embeddings. And these embeddings in turn can be used by other models to highly accurate prediction of molecular energy characteristics. For training neural networks, a large and informative dataset is crucial. A 300,000 molecules subset of QMAX was selected by us, and these figures demonstrate the characteristics of the obtained subset. And for each molecule, we calculated the corresponding matrix element of kinetic energy K using this formula. And the electron density matrices D were already included in the dataset. As the base architecture, we used a message passing neural network, also MPNN, which enables converting node level information into global graph level representation of the molecule used for property prediction. The first stage involved creating a model to produce physically informative embeddings, and to do this, the MPMN received the molecule structure, including atomic numbers and bond multiplicities, and produced embeddings for each atom and for each bond. And those embeddings were fed into two fully connected networks trained to predict the KD contribution from each atom and bond. And after aggregating all contributions, the loss was computed and used to update the model weights. The second stage involved training on these embeddings to build a KD model for separately predicting the total and kinetic energies of the molecule. At this stage, two fully connected networks, MLPs, were used, one for predicted atomic charges, and the other for predicting coefficient C0 to C13, which were then used to approximate the interatomic potential using formulas this. Molecular geometry was additionally used as a source of information. And in this case, the model learned to predict the difference between the linear regression baseline based on atom types and counts and the reference energy. This is results. This figure shows the training progress and loss function decay. And on the next figures, we can see validation errors on the total energy prediction and the kinetic energy prediction. So mean absolute error was 6.1 and 2.1 kilocalorie per mole respectively. To test the model, we perform an experiment on predicted interaction energies between DNA base pairs. The developed model demonstrated results comparable to other methods, like some empirical GFN 2xTB and the another popular model for predicting molecular energy, ANI. And it's close to the reference values. Deviation from known values were 2.4 kilocalorie per mole for a TAP pair and 5.1 for a GC pair. The next step was to access interaction energies in the larger set of 66 molecules, account for basis function overlap effects. The figure shows that the model produced correct results for molecular interaction energy prediction. And though interaction energy was not the primary target during training, the model still demonstrates an ability to predict energy parameters consistent with reference values with a root mean square error of 1.7 kilocalorie per mole. And in the final test, we evaluated the model sensitivity to molecular conformation. And for 4,000 conformers, their relative energies were predicted. And as shown in figure 13, the model achieves a good correlation in predictive relative conformer energies with a root mean square of 1.4 kilocalorie per mole, and it outperforming the both GFN 2XTB and ANI. And to verify the physical validity of the predictions, we analyzed the Lennard-Jones potential parameters. The distribution shown in this figure of sigma and epsilon indicates that magnitudes are comparable to those that used in classical force fields like GROMOS. The predicted charge distribution for 1000 molecules shows that the most values lie within plus minus 0.25 electron charges, supporting the physical plausibility of the model's prediction. And this figure shows the composition of total energy into contributions, Coulomb interaction, Lennard-Jones interaction, and short-range interaction of covalently bonded atoms. So let's go to the conclusions. A two-stage approach of training neural networks was proposed and implemented to the model of dependence of biomolecular energy on spatial structure and quantum mechanical descriptors. The developed models demonstrate the ability to generalize to tasks beyond the direct training objectives. And it was shown that based on the molecular structure and components of electronic kinetic energy obtained from DFT, it is possible to construct feature vectors analogous to atom types in classical force fields. A graph neural network was developed to compute these vectors for all atoms in biomolecules. And interatomic potential form was proposed with parameters dependent on atom-specific features derived from the graph neural network. A fully connected model was used to approximate both molecular energy and electronic kinetic energy, with mean absolute errors of 2.2 and 6.1 kilocalorie per mole respectively. The Lennard-Jones potential parameters and effective atomic charge predicted by the neural models were consistent in magnitude with those used in classical force fields like GROMOS. And the two-stage neural network model enables prediction of biomolecular conformer relative energy with a root mean square error at 1.4 kilocalorie per mole. And the applicability of interatomic potential derived from the structural formula was confirmed for predicting energies, interaction energy of in 66 complexes with a root mean square error of 1.7 kilocalorie per mole. Thank you very much for your attention. If you have any question, I'd be happy to answer them.
Very interesting talk about, as example, mass processing in the organic chemistry and chemistry, physical chemistry. Okay, dear colleagues, do you have any questions? Yes, we have any questions.
I'm sorry, the connection, the sound quality is very poor. I can barely hear you.
Thank you for your presentation. Can you hear me?
Yeah.
With your, thank you. I have two questions. The first, you mentioned the time advantage of this neural network calculations. How long did it took to estimate the parameters of the molecule with neural network in comparison to classical quantum methods?
Using neural networks, the prediction time lays around milliseconds, even not for only small molecules, and it's the same for big complexes of like tens and hundreds of molecules.
Okay. And second question, did you try the principal component analysis on data set? And if yes, what were the results?
Can you repeat the beginning of your question, please?
Did you try the principal component analysis or PCA on your data set before calculation of this network? And if yes, what were the results?
Mm. I'm sorry, I can't hear this word. The principles of what?
Principal component analysis,
Like
PCA.
the
It's widely used in machine learning to reduce the number of parameters to neural network to work with. If not, that's okay.
I think no.
It answers my question.
Yeah, I think no.
Any questions online? Okay. Our next presentation will be online. Dr. Chorny from National University of Life and Environmental Science. Please, Natalia, are you here?
Good morning. Can you hear me?
Good morning. Yes.
May I check my presentation scrolling or not? Is it okay?
Yes, it's okay.
Oh, thank you very much. So let me start. Dear colleague, I want to present our findings about the interface role in the determination of the properties of luminescence oxide glass ceramics. This work was performed by a scientific group, which include experimental, theoretical, and chemical experts in these fields. So our motivation for the study connected with a wide range of the application of the glass ceramics. Here you can see optical devices, electronic devices, medical applications, and in building and construction. I limit our presentation only to optical properties of the glass ceramics as very interesting ones. To show you that glass ceramics have different properties than its constituents. First of all, I should to say that glass ceramics consist of amorphous host or matrix and also with crystalline filler. In our case, crystalline filler have luminescence properties, and glass host is oxide glass. In the right part of the slide, you can see that luminescence spectra of the crystal in black and glass doped with europium in blue completely different from the glass ceramics shown in red. Why this happens? It is because interaction between glass and crystal. So we can say that interaction between these two parts produce new unique properties, in particular luminescence one. Between scientists, there are some discussion if we should we say it is interface or interface. It's two different terms. First means the surface between two phases. It has no thickness, no volume, no mass, and probably no great effect on the materials. But if we talk about interfaces, we have thickness, volume, specific chemical composition. So I should say that interface is very, very important term. How the interface is formed? When we put some crystal into oxide glass, because of diffusion of atoms between crystals to matrix and vice versa, we obtain some region where chemical composition is different from matrix and crystals. More crystalline particles we introduce into host, more interface region in volume we obtain, and less smaller crystal produce more interface. The problem is to experimentally obtain evidences of the interface effect on the material's performance. For the date, we found two methods. They are complex to confirm the presence of the interface. It's transition electron microscopy and small angle X-ray scattering. But in our study, we propose to use combined theoretical and experimental technique based on luminescence spectroscopy and molecular dynamics simulations to confirm and predict manifestation of the interface in oxide glass ceramics. We also produces two oxide system as experimental samples based on phosphates and borate glasses and molybdate and vanadate crystals. We use luminescence probe method and also classical scanning electron microscopy, X-ray diffraction, infrared absorption, and diffuse reflection spectroscopy, in addition to luminescence spectroscopy to characterize our samples. Here you can see glass crystal and also glass ceramics on the same images. We can see that crystal incorporated into glassy host. So we can say we have experiment with glass ceramic samples. The first observation of the interface effect we can see from diffuse reflectance spectrum. As at short wavelengths part of the spectra, it is seen that green and red curve practically coincides. It means that in this part, glass ceramics have the same performance as the glass, but at the longer wavelengths, the difference between glass and glass ceramics is clear. We used infrared absorption spectroscopy in order to find what molecular anions, molecular groups are present in our glasses and glass ceramics. So we can find here the vibration of the phosphate tetrahedra, molybdate tetrahedra, and also condensed tetrahedras like pyrophosphates and such molybdate groups. At the next step, we used molecular dynamics and the results of the infrared absorption in order to fill unit cell with specific composition. Part of the unit cell was filled by crystal, and another part was filled by molecular fragments listed here. And we tried to take some ratio between molecular fragments in order to meet the composition of initial glasses. And as one of criteria for confirmation of our modeling is comparison with experimental data, in particular XRD pattern for experimental XRD pattern for the glass and fuel composition modeled by molecular dynamics. As a result of molecular dynamic, we obtain a distribution of the atoms within unit cell along the z-axis. And comparing atomic structure before and after molecular dynamics, we can distinguish an interface region. And in the case of borate system, we estimated the thickness about 2.8 nanometers. This value is very close to the reported for another oxide systems, glass ceramics, obtained by complex techniques. From this region, we can obtain the chemical composition of interface and use it for further calculation by DFT approach. The similar results was obtained for phosphomolybdate system, and DFT-based calculation were performed on smaller unit cell because it's more precise but more complicated and time-consuming approach. We obtained optimized atomic structure, partial density of states, and some optical properties. Analyzing the content, the surrounding of some cations in the optimized system allowed us to see that in interface we have more distorted polyhedra and more defect polyhedra. So we assumed that bismuth ions can be in other charge states than its typical 3+. It's our assumption was made according to the luminescence spectra and also to literature data. As a result of the combined study by molecular dynamics, by DFT approach, by luminescence spectroscopy, we obtained the possibility to ascribe specific bands in the luminescence spectra to emission of the bismuth ion in various charge states. So here we have some correlation between number of bismuth surrounded with high number of oxygen and so on. The similar result was obtained for borate system. Here we can see that glass have much more vanadium O5 groups comparing to interface and comparing to crystals. So in glass without rare earth ions, the luminescence may be caused not only by vanadium O4 groups, but also by vanadium O5. Another interesting result that we have less distorted polyhedra for lithium. That means if europium ions or other rare earth ions introduced into glass occupy this position, we should have spectrum of europium ion emission similar to this crystal, to europium in these crystals. And we see the predicted result in the luminescence spectra. Really, the middle part correspond to interface, to luminescence center in interface. It is close both to crystal and to europium in glass, but some specific peaks can be ascribed as typical to glass ceramics and crystals. Another interesting result we obtain in direct calculation is possibility to explain the absorption of the materials, glass ceramics and glasses in the visible region. So our calculated optical absorption spectra and the experimental absorption spectra have bands in the visible regions that can be described to transition from oxygen states to vanadium states. And so I want to say that combination of experimental and calculation techniques allowed us to explain interface role in the macro characteristic of the glass ceramics. We used many techniques, many systems, and this combined method can be expanded to not only phosphate and borate system, but maybe some other oxide systems. And I think it's all, and want to say thank you for your attention, and I'm ready to answer some questions.
And I have one question about what chemical species even.
Oh, I'm sorry, very.
Yes, my questions corresponds to what chemical species in your composites influence and what do you use sensing problems?
Oh.
Thank you.
If I am hear you right, in our luminescence, in our samples, the luminescence centers are bismuth ions, also vanadate molecular ions, also borate, a little, but maybe borate groups, and the main luminescence center in europium dopant system is europium 3+ ions.
Then in cationic forms.
Yeah, mainly.
Metal cations.
Yes, mainly cations, but in undoped glasses, like glasses without europium, also vanadium O4 groups play a great role.
Thank you very much. Dear colleagues, ask questions for me in call.
Thanks, Vitali, for your nice presentation. If you have a question concerning the preparation of the composition, which temperature is enough for you to obtain the phase of the glass and
if we talk about the experimental samples, we used melt quenching technique, and highest temperature was for phosphate molybdate system is about 900s, and for borate system 800s. If we talk about the molecular dynamics, we described the procedure in our recent publication, and here we use temperature up to 5000 of Kelvin, but for very, very short duration, like few femtoseconds.
Okay, thanks.
Thank you very much. And we have some questions online. No questions. Okay. Thank you very much. Thank you very much. Our next presentation will be on site. Dr. Mikhailo Kurmach from Visarjevsk Institute of Physical Chemistry and NASA of Ukraine is.
Something like super strong, especially because the main source of molecules and sugars are very important as very important source of reactants. From glucose, we can obtain different molecules. For example, fructose, lactic acid, methyl lactate, ethanol, levulinic acid, hexane, formic acid, and other materials for us is interesting lactic acid and their derivatives, such as methyl lactate, which can be used as monomer for biodegradable polymers in food industry, in pharmacy, different glucose as a scaling agent for hard water, and as methyl lactate, we use it as solvent for different molecules. Typical synthesis of lactic acid for methyl provides using different ferments. Last time, developed different methods for obtaining lactic acid or methyl lactate from glucose using isolate analysis, specialist and the high. But it should be noted that the highest yields up to now is around 50%. So the development of new active catalysis for obtaining methyl lactate or lactic acid from glucose is very important. In our work, we investigated two types of maybe three types of standard metazoites that compared with each other. The first it are typical standard metazoites obtained with so-called conventional zeolite TOH as a structure direction edging. The second approach consists in using so-called Gemini type supercounts as structure direction agent. We use two different structure direction agents. This approach allows to obtain materials with high external surface, but the price of these materials are quite high. So we investigated the third approach when we use typical for synthesis conventional standard metal zeolites with different mesoporohens. As mesoporohens, we use predominantly ionogenic ionogenic supercounts, such as the boronic, such as the polyethylene glycol and polyethylene acetate, and some cationic surfactants, such as the mini-type surfactant to compare with other methods, and lower sulfide. Among all mesoporohens, we have determined that only two mesoporohens give us a mesoporohylate. That is polyethylene alcohol and polyvinyl alcohol. So we concerning our focus, our next investigations on determining the influence of amount of polyvinyl alcohol on the external surface and their catalytic activity, basic properties, and so on. So as we can see, a fixed standard contact interaction increase in concentration of mesoporogen allows to increase in mesoporous volume, in colors of mesoporous volume, and external surface properties. We use two different types of polyvinyl alcohol with different molar weight.
in both cases, we have obtained a similar trend. Or at fixed mesoporohan volume hydrogen to see interaction nature with increase in stannum concentration. We also obtain the similar trend when with increase of stannum interaction increased the volume of mesopores, mesoporous volume and external solid. Acidic properties of such which we investigated for the different results. For example, for Gemini type substance, we have trend of increasing of Lewis acid centers, which are typical for the materials of such types, and also which are increasing with increase of stannum in final samples. Also, as there are two conventional, a small amount of sites, which are terminal stannum groups, we also observe. In case of polyvinyl alcohol, we observed the same trend for PVA with lower molar weight. In case of higher weight of polyvinyl alcohol usage for synthesis of the light, the highest concentration of pollutions was achieved for samples with 1.5 molar% of CO. Further decrease in concentration of samples. This time we think that it would be due to a significant decrease of masculinity of final sample obtained by in this one. Catalytic activity of samples we investigate in the process of obtaining methyl lactate from glucose in methanol. It should be noted that in water we have obtained acid, in methanol we have obtained methyl. As we can see, for all so-called gene capture, the light conversion is around 100%. Is full. Well, selectivity and corresponding yield significantly differs from one to another state. For example, for conventional lights, we demonstrate that selectivity is close, but the trend is that selectivity decreases. In case of the highest selectivity was achieved by samples stannum 75, 1.5 molar%, which have the highest concentration of ACE inside. In case of SDL1, we have a trend of increasing concentration of ACE sites and increasing of selectivity in the target. Comparing different zeolites obtained at with different methods, we demonstrate that the highest yield, highest selectivity was achieved for the samples obtained with polyvinyl alcohol. Other time for the others, for enhanced selectivity varies around 20 from 20 to 40%, and this material from so yield is lower. Comparing catalytic activity of samples obtained at different and different amounts of stannum in the sample. We have mesopropane interaction, We have confirmed that we have the next event for these at constant measurable and reaction mixture with increase of time. The highest conversion was highest yield was achieved for the samples obtained at with 1 molar percent of standard in a sample. Whereas for at this Nano-2025, we have another friend, which, as we can see, the highest yield was achieved for PVA with samples obtained with PVA 65,000. At the highest yield of standard, highest yield of not standard, highest yield of azote. Whereas for a PVA 176,000 has for the highest yield was achieved for the samples with PVA C05. The further decrease of yield for the samples was predominantly maybe decrease of the active sites and the decrease of the. So in this work, we investigated standard methods obtained by 3 different methods, and we have demonstrated we can obtain zeolite with high selectivity to material effect using in case of diminished we can obtain materials with relative cheap.
Thank you very much for your talk. I have one small question about what do you think why polyvinyl alcohol increase in the selectivity or
increased mesopore volume and increased amount of acid side. Yes. And conversion and selectivity talking about. Mesopore handling the possibility of the calcination process. It influences on structure. Yeah.
Thank you very much. Dear colleague, do you have any questions to our speakers? No questions? Okay. Online, no. Thank you very much. Our next presentation will be online. Dr. Darina Yadvinka from Institute of Molecular Biology and Genetics, Kyiv, Ukraine. Darina, are you here?
I can hear you. Do you hear me?
Yes.
Can you see my presentation?
Yes, they see, but not full screen.
Yes, yes. No? Is it
No.
okay?
No, you should stop sharing the screen and then choose the windows with full screen mode.
I already do this. No?
Oh, please. No. You got start sharing and then choose the full screen. But you should do it in the opposite side. You should stop sharing now. Screen.
Okay, let's start. Now?
You are not stop sharing. You're still sharing the screen. Please click the button stop sharing in the Zoom. Now start your presentation in full screen mode, and only after that you should start sharing.
No.
You start sharing, and only now you try to start the slide presentation, but you should do it in the opposite order. First, start the presentation, then start sharing the screen, reach the full screen. Okay, let's do it in this way because we're a little bit run out of time. It's quite a good thing in our screen, so you can start.
You can see the full screen mode, yes?
Unfortunately, no, but it's quite big, so
Sorry,
probably
I
you
don't
can
understand how to fix it. Okay, I will be start like this. So, dear colleagues, today I'll be talking about the development of highly sensitive method for bisphenol A detection using a fluorescent sensor system based on molecularly imprinted polymer chips with embedded silver nanoparticles. Let me begin with some background. Bisphenol A is a synthetic compound widely used in the production of polycarbonate plastics and epoxy resins. While BPA is also a well-known endocrine disrupting chemicals, and the exposure to BPA is associated with reproductive and developmental disorders as well as neurotoxicity. Moreover, now BPA is also considered as a priority environmental contaminant, which can be often detected in surface water, drinking water, sediments, posing risk to both human health and ecosystems. In recent years, BPA international regulations on BPA levels it's become more stringent. Traditional methods for BPA detection, such as HPLC and mass spectrometry, are accurate and reliable, but they also have some serious drawbacks, such as they require sophisticated instrumentation, trained personnel, and time-consuming procedures.
Daria, we see only one first slide.
Oh. I'm sorry, because I see the full screen mode and
See no full screen and see only first slide.
okay.
It's because you start sharing after sharing the screen with us. Stop the full screen mode after you sharing the screen with us. So please work in the windows with not full screen mode. So we will be on the one side.
Do you hear some screen?
Now we see the fourth slide. So if you will work on this window, it will be on the same page. Click next. Yes, now we can see the fifth slide.
Okay, I will continue with this slide.
Okay, please.
So it is a clear need for fast and affordable sensitive sensor-based method for bisphenol A detection. And one of the most promising approach is to develop a biosensor-based concentrated sensing receptors, in particular molecular imprinted polymers. These materials are stable, cost-effective, and as well as antibody are capable of specific molecular recognition and detect our target molecule with high selectivity and specificity. Moreover, the analytical sensitivity of such sensor can be significantly improved by integrating plasmonic nanomaterials such as silver nanoparticles, which can enhance the fluorescence sensor response through plasma-enhanced fluorescence phenomena. So the aim of this study was to develop a highly sensitive fluorescence-based sensor system for bisphenol A detection using molecular imprinted polymer chips with embedded silver nanoparticles. Here is the process of molecular imprinting technology, which begins with formation of the polymerization mixture which contains a template molecule, bisphenol A, a functional monomer, ethylene glycol phosphate, crosslinker, and silver nitrate. After polymerization, the BPA template molecule is removed, leaving behind specific binding sites that are complementary to BPA in their size, shape, and functional group orientation. Moreover, the silver nanoparticles are formed in situ during the polymerization process and reduction of silver nitrate within the MIP-film structure. And finally, MIPS immobilized glass slides, and we obtain MIP chips, MIP sensor chips. First of all, silver nitrate concentration were optimized in monomer mixture. Here you can see the fluorescent sensor responders as a function of silver nitrate concentration added to monomer mixtures. And we observed both the fluorescent enhancement and quantum effects strongly depend on the amount of silver nitrate concentration. And the best signal enhancement effect was achieved with addition of 1 millimole of silver nitrate, and we observed the signal more than 3 times higher than that for silver nanoparticles free mix. So this silver nitrate concentration were used for further MIP chips synthesis. To verify the formation of silver nanoparticles formed in the structure of MIP films, we performed transmission electron microscopy, and we observed the spherical nanoparticles evenly distributed in the MIP film's structure with a size of 20-30 nanometers, which is optimal for plasmonic enhancement in our system. Here you can see the calibration plots for bisphenol A detection using our MIP chips, and the limit of detection for silver nanoparticle modified sensor system was assessed as 10 nanomole, and the linear dynamic range was from 10 nanomole to 25 micromole. And moreover, as compared to our previously developed as a colorimetric MIP-based sensor with a limit of detection like 5 micromole, this present plasma-enhanced fluorescence sensor system system reduces the limit of detection to 10 nanomole with improvement of approximately 500 folds. Here is the result for selectivity study. As shown, our MIP-based sensor demonstrated significantly high selectivity towards bisphenol A as comparison with its host structure analogs like phenol, presols, nitrophenols, catechol with ursonols, and so on, which confirming the high selectivity of the recognition sites in the structure. And finally, proposed sensor system was successfully used for the determination of bisphenol A in spiked wastewater samples. You can see these results confirm the successful application of our sensor system for bisphenol A detection which can be effectively applied for analysis of BPA in complex environmental matrices. To summarize, molecular imprinted polymer film-based sensor chips containing embedded silver nanoparticles were successfully employed for the development of a novel, highly sensitive system for bisphenol A detection and monitoring. The developed sensor demonstrated a detection limit of 10 nanomole and the linear dynamic range from 10 nanomole to 25 macromole. Sync films mobilized on glass slides exhibited significantly higher selectivity towards PPA compared to structurally related similar compounds. The sensor chip also was successfully applied for the determination of BPA in spiked wastewater samples, confirming their applicability for real environmental matrices. And the proposed sensor system showed excellent reproducibility, high selectivity, and reliable screening for BPA contamination. Thank you for your attention. I'm sorry for these technical problems, and I will be happy to take any questions.
Darius, thank you very much for your talk. Please, my colleagues, do you have any questions to Daria? No, no questions in online, no, online too. Okay, Darius, thank you very much.
Thank you.
Our next speaker will be online, Larissa Kumitska from Institute of Macromolecular Chemistry, Ukraine. Please, Larissa, Dr. Larissa, please. Are you here?
Yes, I'm here. But I just want to try to upload my presentation. I don't know. Is it okay?
Not full screen.
Is it okay or not?
No.
No?
No,
You
not
don't
full
see my
screen.
presentation?
We can start your presentation.
Not-
You sent
What
to
should
us yesterday.
And I don't know. Okay.
Miss Larissa, we have your presentation on our computer. We can share it for you
Yes.
if you want. Okay?
Yes.
So one moment, please. We will do it soon.
Yes, please.
If you can see your presentation, you could start. And please tell us when to please slide. Larissa, are you with us? Larissa, can you hear us? Looks like Dr. Larissa has a problem with the internet. One moment, colleagues. We will try to find Dr. Larissa Konitska. No, she is not in our conference room now. Probably she will reconnect later. Then we can move forward to our next speaker, Dr. Vasil Yashchuk, and then return back to Larissa Konitska. If Dr. Yashchuk ready. Dr. Vasil Yashchuk, can you hear us?
I am here.
So if you're ready, you can start sharing your presentation.
Yes, yes. Yes, moment. You can see? No?
We can see your presentation. And when you're ready, please start it.
I don't understand. My presentation is visible? No?
Visible, but it's not the first slide.
But it's not. What?
We can see your presentation, but it is not the first slide. Please start from the beginning.
Second. Yes?
Okay, now we can see the first slide, so please start.
Yes. One moment. My presentation is temperature-controlled random blazing of dyes in aqueous suspension of coral shell nanoparticles. This research was carried out at Taras Shevchenko National University of Kyiv in collaboration with Professor Gulchansky, Schengen University. Motivation of the work is next. Development of optical nanotechnology sensitive to spatial temperature change in biological objects, detection of areas of elevated temperature, and mapping of temperature distribution in biological objects using optical technology. Subject of the investigation is random blazing of rhodamine 6G in aqueous suspension of polymer nanoparticles with temperature-dependent effective refractive index. To get to heat of the matter, I would like first to introduce the features of random blazing. Random blazing is inherent to an active media with multiple scattering. It evolves along random trajectories in the scattering menu and does not require any other optical elements. Therefore, it is suitable method for detecting and mapping of scattering medium. The emission spectrum narrows with increasing of excitation to value typical for conventional dye lasers. And the spectrum width and intensity depends on the concentration of scattering centers. This plateau indicate this narrowing to this plateau indicates the random blazing is rise in such media. On the right figure, there are the results of Monte Carlo simulation. This demonstrates the visualization of scattering clusters in a dyed medium as areas of increased brightness due to the occurrence of random blazing in them. These clusters, this picture of distribution of brightness, random blazing. Each spot corresponds to same clusters on this model. The next slide demonstrate this construction of core shell thermosensitive nanoparticles. In order to achieve thermal sensitivity of random Lensing, these nanoparticles was fabricated. This particle consists of hydrophobic core and hydrophilic and thermosensitive shells. This is core consists made of polystyrol and shell from this polymer. This slide demonstrates how these nanoparticles react on heating. This under heating, the hairs of the shell twist and shell contracts to the globule and squeezing out the water. Effective refractive index consists of the part of the refractive index of core, refractive index of shell, and water. When coil transforms to the globular, part of the water decrease and effective index increase too. As a result, the scattering efficiency of these core shell nanoparticles increased too, and the suspension of these nanoparticles become transformed from the transparent to cloud. The next slide. The size of these nanoparticles determined with the DLC method. This slide demonstrates main detail of this method. Smaller particles fluctuate under brownish motion frequently and more the nanoparticle with more size fluctuate more slowly. This intensity function for suspension of nanoparticles gives function of fluctuation intensity. Correlation of this function gives a correlation function. From this data, one can see that correlation function decrease and in the time. This time depends on the diameter of the nanoparticles, and from this one can know so-called hydrodynamic diameter of the nanoparticles. The next slide demonstrates the result of measuring of the dynamic diameter of particle as a function of temperature. It can be see that this diameter decreases almost linearly in the range of about 45 degrees of Celsius. The sensitivity of this change is about 8 nanometer per degree. The next slide demonstrates the simplest, the diet samples of aqueous suspension of core shell nanoparticles with rhodamine 6G. These suspension are able to change their transparency with the temperature. As the temperature increases, they become scattering, which is necessary for random lasing. The next slide demonstrates experimental setup for recording the emission spectrum of diet suspension of core shell nanoparticles as a function of the pumping intensity and temperature. Pumping was performed by the second harmonic of neodymium laser. At the same time, the transmission of the suspension was measured using this semiconductors continuum laser. This is sample which is heating and thermostating with more big volume of water. And under experiment, this thermostat stirrer, this water in thermostat stirrer. The result recorded on the computer as a spectrum, one shot resisted by diffracted spectrograph. The next slide present the result of study of random lasing of rhodamine 6G in aqueous suspension of core shell nanoparticles. It can be seen that with increased pumping, the emission spectrum narrows and reach a shell, which indicates the occurrence of random lasing. It can be seen that with this increase in pumping, the emission spectrum spectrum of the random lasing is approximately an order of magnitude narrower than the luminescent spectrum of rhodamine 6G, which is consistent with the typical width of the spectrum on conventional random lasing. The next slide demonstrates the width of the random lasing spectrum depends on the temperature. It decreases at a rate of approximately about half nanometer per degree Celsius. This indicates the principal possibility of using this effect to detect a region of elevated temperature in a medium impregnated with such a suspension. This one. And the last slide. Excuse me. And the last slide demonstrates that the temperature dependence of the spectrum width of the diarandom lasing in the suspension of thermosensitive core shell nanoparticles correlates well with the similar dependencies of the suspension transmission and the hydrodynamic diameter of this particle. And the last, the main result at conclusion. Aqueous suspension of the core shell thermosensitive nanoparticles was tested as active medium for random lasing. Core shell thermosensitive nanoparticles were synthesized and characterized. Their hydrodynamic diameter decreased from 340 to 100 nanometer in temperature region, in this temperature region. Thermosensitivity is about half of nanometer per degree of Celsius. Dies and percentage composition of nanoparticle suspension suitable for random raising is obtained were selected. It is shown that in suspension of such a composition with rhodamine 6G, random raising excited, the parameter of which spectrum-wise and intensity at its maximum depend on temperature. Temperature sensitive of random raising can be estimated by the rate of about half of per degree of Celsius. The narrowing of the emission spectrum, which is main attribute of random raising, correlate well with the decrease of the transmittance and volume in which raising is excited. The result demonstrates the suitability of diode suspension of thermosensitive shell nanoparticles for detecting special areas which with elevated temperature and mapping of temperature distribution in the sample. Thank you for attention. This is all.
Thank you very much for your interesting talk. I have one question about what is the size of the core part of your current shell type structure? Core. What size is the core part?
This one.
Yes, the core.
Oh, this. No. I am waiting for your question.
You have core and shell. What's the size of the core, Kamal?
Size of core is about from 40 to 90 nanometers. And
from 40 to 90 nanometers. Okay, thank you. We have one more question in our conference call.
I have
moment.
Thank you for your presentation. I have a question regarding how much can a concentration of core shell nanoparticles in solution affect their thermal sensitivity and other parameters you found?
The presentation of the nanoparticles in suspension is not determined exactly. This concentration select to reach the opaque of the suspension at higher temperature. This is next methodology to detect how much is concentration of the nanoparticle in this wax solution. And I don't know how much.
Okay, thank you very much for the answering. The answer is clear. And I think we will go back to our previous speaker. Thank you very much once again, Professor Yashuk. And we will back to our previous speaker who had a problem with internet connection, Larissa Kunitska. Dr. Larissa, can you hear us? Are you with us?
Yes, I'm.
Okay, now we will share the presentation for you. One moment. Okay, do you see your presentation?
Yes.
Okay, you can start and then tell us when to switch the slide.
Okay, so hello everybody, hello colleagues. Today I would like to present the results of experimental work which was carried out by the Institute of Macromolecular Chemistry of Kiev in collaboration with Paul-Sabatier University of Toulouse, France. Today we'll talk about hybrid polar-ion complexes and their possible application in catalytic processes. So, how bimetallic and multinuclear catalytic systems have demonstrated superior performance and key transformations such as oxygen reduction, hydrogen evolution, and CO2 reduction, where electron and proton transfer mechanism are essential. Understanding and optimizing these interactions leading to improved reactant activation, electron transfer, and intermediate stabilization provide valuable insights for the design of highly efficient catalytic systems. In this context, the use of copper-based hybrid polyion complexes may be of particular interest. Probably I will ask you to change the pictures, please. Yeah. Let me remind that hybrid polyion complexes called HPICs are formed when water-soluble block of polymers comprising ionizable complexing block and neutral block interact with polyvalent metal cations in water solution. Such complex formation resulted in stable nano-objects with core shell structure consisting of a core rich in complex ions and hydrated shell formed by the neutral blocks. Next, please. There was reported the formation of stable hybrid colloidal suspensions when mixing multivalent metal cations with double hydrophilic block of polymers containing polycarboxylic acid block or polyphosphonic acid block. Such systems have been employed as highly efficient contrast agent or as templates for the preparation of metal hydroxide, oxide, or sulfide nanoparticles. HPICs loaded with copper or iron have been also been successfully used as homogeneous catalysts for the degradation of naphthol blue black via a photophantom-like process. Next, please. In the present study, we investigate colloidal structures based on hybrid polyion complexes formed by the complexation of copper ions with double hydrophilic block of polymer comprising neutral polyvinyl pyrrolidone block. You can see this scheme of complex formation. And the ionizable polyvinylamine block for the PVP, PVA. And we evaluate the ability of mentioned HPICs to promote synergetic effects in O2 activation reactions. It's necessary to say that polyvinylamine is a water-soluble polymer with high content of primary amine groups, which easily complex with metal ions. So the use of polyvinylamine instead of more commonly used polyacrylic acid is expected to enhance interactions with copper ions. PVP-PVA block copolymer was obtained using rough techniques. You can see a scheme in the picture. In the first step, PVP macro chain transfer agent PVP-ST was prepared, and then, unfortunately, I don't know if it's. Can you see if it's seen? Is it seen if I show? Hello.
We can see only your slide. Your mouse moves.
Only slide, but I cannot point the. Okay.
Yes, because it's our screen share. If I know where to point, I can do it, but I don't know, and we will waste too much time if we do it.
Okay. Okay. On the next step, on the next step, PVP-ST was used as a macro agent for the polymerization of vinyl formamide, and then polyvinyl formamide block was fully hydrolyzed under basic conditions, forming the polyvinylamine block. Next, please. To understand the peculiarities of HPICs formation, increasing amount of copper sulfate was added to the constant amount of block of polymer so that the molar ratio between copper ions and amine groups of polyvinylamine block changed from 0 to 1 to 0.2. Obtained compositions were examined by UV spectroscopy and conductometry. As the formation of the complex was confirmed by the presence of a band with lambda maximum 594 nanometers, figure 1a. Above a given concentration of copper sulfate, a new band was observed at about 800 nanometers, which means the appearance of free copper ions. Then absorbance was plotted as a function of ratio between copper and amine groups to determine the stoichiometry of the complex formed. This is figure 1b, black line. A change in the slope was observed at ratio 1:4. This result was confirmed by the conductivity, figure 1b, blue lines. While the conductance of pure copper sulfate solution increased linearly with concentration, the conductivity of the polymer containing solution remains constant up to ratio 0.2 and then increased with a slope comparable to that of the copper sulfate solution alone. Hence, absorbance and conductivity measurements highlighted the formation of complex, which is complete complexation when the ratio between copper and amine groups of polyvinyl amine blocks is close to 0.2. It should be noted that the same result was previously described in the literature for the complexes between polyvinylamine homopolymer and copper. Next picture, please. To obtain the kinetics of copper loading at molar ratio 1:4 between copper ions and polymer, we followed the evolution of maximum absorbance as function of time directly after the addition of copper sulfate to polymer solution. Obtained kinetic graph, presented in figure 2a, shows very fast complex formation, which is completed within 5 seconds. The Ashpix formation was also proved by dynamic light scattering, figure 2b. In the absence of copper ions, polymer form polydisperse and large aggregates appear due to Ashpix formation. The diameter of these aggregates at the ratio 1:4 is about 20 nanometers. Next, please. Transmission electronic microscopy shows small, high contrasted domains with an average diameter of about 4 nanometers, figure 3a. These domains presumably arise from the copper-rich complex core, and zeta potential, figure 3b, was measured at 2.9 milliwatt for copper Ashpix, whereas its value for a pure polymer solution is equal to 3 milliwatt. It indicates a slightly positive surface charge. Therefore, the less stem and zeta potential data strongly support the formation of Ashpix as follows. Upon addition of copper ions to the block of polymer, a rapid complexation with PVA block occurs when a ratio between copper and amine groups more than 0.12. These interactions led to the formation of Ashpix nano-objects with a polyvinylamine core cross-linked by copper ions surrounded by a neutral PVP shell. Next, please. It was interesting to evaluate the colloidal stability of Ashpix. For this purpose, copper Ashpix samples were prepared in the presence of different amount of sodium, 1 molar sodium chloride. As can be seen from the UV spectra, figure 4a, sodium chloride doesn't lead to the destruction of the complex, and Ashpix remains stable even at very large excess of sodium chloride.
Sorry for interruption. One moment.
Yeah.
Moment, we will share the screen properly because it was one short disconnection. I will tell you when we will ready, please. Okay, now you can continue. Sorry.
So I will describe the slide, the picture number 8 again. Yeah.
Yes.
From the very beginning, it was interesting to evaluate the colloidal stability of Ashpix. And for this purpose, copper Ashpix samples were prepared in the presence of a different amount of 1 molar sodium chloride. As it can be seen from figure 4a, UV spectra doesn't show any changes. So sodium chloride doesn't lead to the destruction of complex and Ashpix remains stable even at very large excess of sodium chloride. It should be added that DLS measurements also do not reveal any aggregation or decomplexation phenomena. So we can say that stability of ash peaks isn't governed by electrostatic forces, but rather by steric stabilization provided by hydrated neutral corona. Additional experiments were conducted to evaluate ash peaks colloidal stability over a pH range from 9 to 1, figure 4b. With pH lowering, we observed a decrease in copper binding band caused by decomplexation. From pH 9 to 6, the absorbance of ash peak solution remain roughly constant, suggesting the complexes remain intact. Lowering the pH down to 4 led to a significant decrease of measured absorbance. Below pH 4, the absorbances sharply decrease. And UV visible spectra show only a weak band around 800 nanometers corresponding to free hydrated copper ions. These results confirm that the interaction between copper ions and amine groups are driving forces behind ash peaks assembly. Next, please. At the next stage of our experiments, we evaluated whether the obtained ash peaks could be applied in catalytic processes. For this purpose, we selected ascorbic acid as model substrate and studied its oxidation by atmospheric oxygen in the presence of copper ash peaks. The oxidation was carried out with copper to substrate ratio of 1 to 5 in water under saturated O2 at 50 degree. As controls, the oxidation of ascorbic acid without catalyst and in the presence of copper sulfate were also examined. The oxidation of ascorbic acid was followed by the decrease in its absorption at 260 nanometers. As we can see from the picture, in the absence of copper catalyst, the conversion of ascorbic acid is below 5% after 20 minutes. The oxidation was faster in the presence of copper sulfate, with a conversion equal to 40%, and the complexation of copper ions within the ash peaks enabled to reach a conversion to 61% after 20 minutes for a ratio 0.2. Therefore, a copper ash peak seems to positively influence the ascorbic acid oxidation process. This naturally leads to ask, what is responsible for this effect? Is it the special colloidal structure of ash peaks, or it is simply due to copper complexation? Next, please. In order to answer this question, a series of experiments were conducted at constant concentration of ascorbic acid and copper, but different concentration of polymer. Another thing, in this experiment, we keep a constant concentration of ascorbic acid and copper ions, but we change ratio between copper and amine groups inside of ash peaks, inside of copper polymer mixture. Corresponding rate constants were estimated as and plotted as function of amine concentration, figure 7. And it turned out that in the absence of polymer, the reaction proceeds like in the presence of copper sulfate. When polymer is added in insufficient amount to fully complex all available copper ions, its ratio more than 0.25. A slight decrease in the rate constant is observed compared to free copper sulfate. When the polymer amount was enough to complex most of the copper ions present and it induced the ash peaks formation, this is the ratio between 0.12 and 0.25. A significant increase in the rate constant is observed. And as we can see, the most effective catalytic conditions shows ratio 0.14. The presence of an excess of polymer at ratio less than 0.12 leads to complete copper complexation, but prevents the formation of colloidal complexes. In these conditions, the resulting constant values are lower than those of free copper sulfate. Next, please. Another factor that may influence the catalytic effect is the distance between copper ions within the H peaks and the existence of cooperative interactions between copper ions. To verify this assumption, an experiment was carried out using the most catalytically efficient condition at ratio 0.14. To modulate the average distance between copper ions under these conditions, some of them were partially replaced with cobalt ions within the H-peak structure. It's necessary to say that, like copper, cobalt can complex with amine functions, but it doesn't catalyze ascorbic acid oxidation. So cobalt was a very suitable object to modulate different distance of copper ions. As we can see from figure 8a, the best efficiency is observed for the H peaks containing 100 copper ions. In the presence of cobalt ions, catalytic activity is decreased. As it's shown in figure 8c, in general, activity in copper-cobalt H peak systems is systematically lower than that in copper H peak system with the same copper concentration. The nonlinear variation observed in copper-cobalt H peak systems confirm the effect of the distance between two metal ions. Any modification of this distance rapidly induces a sharp decline in catalytic activity. And next picture, please, with conclusion. So, a series of colloidal structures based on hybrid polyion complexes, H peaks formed by the complexation of copper ions or copper-cobalt mixtures with a block of polymer containing vanillamine were designed. Obtained colloids have well-defined dimensions and demonstrate a catalytic activity in reaction of ascorbic acid oxidation by air oxygen. The main factors influencing the catalytic activity of H peaks are copper content and the average distance between copper ions. Modularity of H peaks enable to integrate different metal ions or their combination, thereby opening promising perspectives to get access to multi-catalytic homogeneous system adaptable to different types of transformations such as Lewis acid catalysis and Fenton catalysis. By controlling the spatial distribution and local concentration of metal centers within the polymer architecture, these systems provide a good platform for fine-tuning catalytic behavior and enhancing overall performance. So thank you for attention. That's end.
Thank you very much for the interesting talk. Then I will ask you about the oxidation state of copper cations in your structure. And maybe the oxidation state influences the activity. Compare copper and gold. Thank you.
You see, it's very bad connection. I don't hear you. Well, I don't understand.
The question was about the oxidation state of the copper in your compound. Is what one or two oxidation state of the copper?
Yes, it's two oxidation state of copper, of course. Unfortunately, I don't have the scheme of. Maybe if you want, I can ask via mail, and I can show you the scheme of.
Okay. The answer is clear. That the state was two. We have no time for more questions, so thanks you once again. And we will move forward to our next speaker, PhD student Konstantin Korotkov from the Francevich Institute of Problems of Material Science of North of Ukraine. Konstantin, are you ready?
Yes. I hear you.
Then please share your screen.
Okay. And see?
Yeah, wait.
So, my name is Konstantin
Yes.
Korotkov. I'm from Franz Francevich Institute, and I can send you topic for the polarization properties of the ferrum gadolinium oxide and the ferrum silicon glass nanostructures were determined from the magnetic resistance. The decimeter range of radiation is used by military system or all armies around the world. Modern methods of protecting aircraft from detection are convenient in stealth technology. A set of methods for reduction the probability of detecting objects in the radar field. The main task is to suppress reflectivity. Solving this problem by changing the geometry and configuration of flying objects has led to a significant reduction in their aerodynamics characteristics. Currently, the idea of covering a reflective surface with absorbed paint and varnish materials with special fillers, or scattering micropores materials. Special treated fabrics, etc. is being used. These nanostructures uh, evaporation with electron beam meshing and the character in this slide we see the characteristic of this evaporation, and this pictures is nanostructures with cuprum Kent electrodes for magnetic resistance experiments. The structures properties seen in this slide, the X-ray diffraction can see the uh, metal group is this of iron group. It's not deformation with doped gadolinium oxide, but voices is height. In electron spectroscopy image we have Galov Island and magnetite, but gadolinium oxide is amorphed. In the uh, in the same image we can see this the morphologies of ferrum structures is Iceland. For magnetic resistance in different magnetical fields, we have impedance properties. In these works, we have components of dielectric permeability and calculate with impedance part. The permeability is paroptic in two times 10 power 5, and this is um, uh, these peaks not seen in thickness, height, or equal percolation. The percolation in 33 nanometers for film. For dielectric permeability, we calculate coefficient of polarization or absorption, and we have fine properties. The coefficient of polarization is half per 1 in ferrum gadolinium oxide and the ferrum in glass less per 1. In this slide, we see the coefficient of transmission. This is equal is translate the polarization coefficient to coefficient transmission. And we see the gadolinium oxide load peaks before gadolinium on glass. And the next slide we see coefficient of reflection. This is coefficient is main for stealth technology and polarimetry modulation. And this coefficient less 0 from gadolinium oxide and higher 0 for glass. But in polarization and in stealth technology, this is coefficient can be low 0. This is a conclude table for all coefficient. This is coefficient have frequency of 2.10 power 5, and his difference is conclusion to the highest polarization, and the difference in all parameters. We have conclusion the difference in the numerical values of the parameters. Polarization, transmission, and reflection. The latter are a function of the kinetics property of the fields and the influence of the exchange interaction. In the frequency range 10 power 5 Hz, the permeability dependence have a percolate in the forms of a maximum at frequency fan. Fan is 2 power then 2.5 The formation of this maximum is probably associated with the spin noise effect. The spin noise effect is characteristics of films with less thickness percolation. The experimentally observed increase in the values of the percolation coefficient, reflection coefficient, and polarization coefficient for iron gadolinium oxide nanostructure compared to the ferrum silicon glass structures is explained by the influence of depth exchange interaction. The changes make ferrum gadolinium oxide nanostructures situated for use in modulation polarimetry, resonator systems, and stealth technology. Thanks. Thank you for attention.
Colleagues, do you have any questions? Konstantin in the call. No question online? No question. Okay, Konstantin, thank you very much. I will invite our next speaker, a PhD student, Maria Sosnovska from National University of University.
Yeah, Konstantin, you have a question in the chat, but we are limited in time, so you can make a discussion in a chat with one Politank who asked you about have you provide comparison of your result with metamaterials. Also interested in this question, you can read the answer later in the chat. Now we will move forward to our next speaker because we already advised.
So good day, esteemed colleagues. My name is Maria Sosnovska, and today I'm excited to share our research on the concept of research on the effect of lithium fluoride on the electrical conductivity of fat solutions of hypolymeric DNA. This work was carried out together with my colleagues, Dr. Tim Lazarenko, Dr. of Philosophy Katerina Duk, Dr. Sergei Alexeyev and Dr. Alexander Alexeyev, Dr. Sergei Perepelitsa, and some students, Olga Vlasuk and Anastasia Stitsuk. I would like to start by reminding you that the DNA molecule carries an electric charge. DNA is a highly charged polyelectrolyte with unique physical properties defined by structure. In aqueous solution, it adopts a double helix shape, stabilized at hydrogen bonds, water molecules, and positively charged conjugate ions that neutralize the negatively charged phosphate groups. In living cells, these conjugate ions can be metal ions such Ca+ and Ag2+, or molecular ions like polyamines, and together with histone proteins, they help further neutralize DNA charge. Biocontrol ions are essential for DNA's biological function. Their interaction with DNA is also important for technological application. In this context, studying the ionic conductivity of DNA in aqueous solid solution, such as with lithium chloride, is a considerable influence. The ionic conductivity of the solution depends on the movement of dissolved positive and negative ions. DNA significantly affects the conductivity through contrarian condensation. Positively charged ions from a cloud around the double helix, as you can see, constrained by DNA and water molecules, creating an ion hydration shell. This shell differs from the bulk solution and can be considered an integral part of the DNA structure. Studies show that contrarians can be in the phosphate group localized in major or minor groups of DNA. Their position depends on charge, size, and vibration, forming either direct or water-mediated contact with the double helix. Contrarians with this ionic atmosphere are significantly less mobile than those in the bulk solution, which can be viewed either as a charge continuum or a lattice-like system with an ionic crystal. So recently, DNA has attracted considerable attention as a promising biopolymer for the development of gel electrolytes due to its unique structural and functional properties. The key to this functional lies in the polyionic nature of DNA. The phosphate backbone carries a negative charge, enabling effective interaction with scattering from various salts. In such gels, the salt ion remain immobile within the polymer matrix, providing the ionic conductivity required for electrochemical application. The mobility of these cations largely determines the gel ability to conduct electric current. By varying the type and concentration of the salt, it is possible to tune both the mechanical properties like stiffness or elasticity and the electromechanical characteristics of gel. And notably, DNA containing gel can simultaneously serve as both the electrolyte and the separator. That's very nice. And it's eco-friendly with its important food. So, the aim of our study is investigation of the electrical conductivity of DNA-doped aqueous lithium chloride solutions across different temperatures and concentrations, aiming to determine the optimal composition for their electrolyte application and to develop a theoretical model describing the temperature consideration difference of conductivity. The DNA sample from salmon testicles was purchased from Sigma Aldrich Company. Two series of the samples was prepared. Aqueous solution with all yield 2 milligrams per milliliter of DNA and or O2, O4, O6, O8, and 108. All 1 per liter lithium chloride and identical solutions without DNA. Remix exact volumes of the stock solution and ionized water. To measure the sample resistance, some solution was injected in the cylindrical quartz capillarity containing 3 platinum electrodes, designing a cylinder 1 clearance free, all embedded in the capillarity wall. The measurements were carried out under thermostatical condition using an alternative current of frequency of 50 kHz. The measured resistance contribution from both the sample polarization and the electrodes. So here we can see the experiment revealed the temperature difference of electrical conductivity with the aqueous solution without lithium chloride and with lithium chloride. Above 60 degrees, our theoretical model predicts that DNA undergoes a phase transition like melting, causing a sharp increase in conductivity in the DNA containing samples. For solutions without DNA, no such change is observed, supporting the hypothesis and the conductivity increases when linked to DNA melting. And additionally, conductivity gradually increases with lithium chloride concentration for both solution with and without DNA. Analysis of the Arrhenius plot formula shown on the slide with the DNA solution without added cells reveals 2 inflection points, dividing the graph into distinct linear regions. These segments correspond to the DNA double helix melting process. Region 1, it's for blue line, 25-50 degrees, represents the intact double stranded DNA, where region 2 is green line, 50 to 70 degrees, reflects the denaturation of DNA macromolecules. So for DNA solutions without added salt, the linear regions are less distinct as the inflection points are less pronounced. This effect is attributed to additional neutralization of the negatively charged groups of the DNA backbone by salt ions. For the calculation of the activation energy, the temperature depends of the electrical conductivity was approximated using the formula shown on the slide. And is the volumetric logical concentration, delta means the pass of an ion, mu is the ion charge, and mu is the average molten frequency. About 10 equal delts, and level E is the activation of force. Different segments of the Arrhenius plot correspond to different activation energy of ionic motion in solution. From the slopes of in region, we determine that in salt-free DNA solution, the ultralinear energy below the melting temperature in region 1 is nearly the same as in the transition region was about 15 kilojoule per mole. And this results valid link with theoretical state. For DNA solutions with added salts, the activation energy in different regions are relatively close to each other. Compared to salt-free solution, they shown only a slight increase. This indicates that lithium fluid concentration up to 1 mole has little or no effect on the remains within experimental to that of the pure with and without lithium fluoride. So the conductivity of the DNA of the solutions of lithium chloride solutions with and without DNA, we calculated the difference in conductivity, as you can see. The data demonstrates that the electrical conductivity of the salt solution without DNA is consistently higher than that of the DNA containing solution. Adding DNA reduced the conductivity of the lithium chloride solution, which can be explained by the partial substitution of hydrogen blood ions by lithium ions in the vibration shell of DNA molecules. This process lowers the number of free charge carriers in the solution. With increasing temperature, the conductivity of the DNA lithium chloride solution further decreases the terminal denaturation of DNA. As the double helix melts, its ability to deal with little plus ions spreads, and thereby reducing the concentration of free ions even more. The concentration range of ozone for ozone in molecular conductivity remains nearly constant. However, at 1 molecule, the conductivity of the pure lithium chloride solution increased sharply compared with that of the DNA in the clean solution. At the lowest concentration, the conductivities of these two solutions are nearly identical, suggesting that the amount of lithium plus ions in contributing B is the separation distance between elementary charges along covalent molecule, and LB is the Buron length. So LB determines the distance at which the interaction energy between two elementary charge equals to the energy of thermal motion magnetic field. According to the simple covalent model, the parameters that are all can be estimated by the following formula that you can see on the slide. It's C here is for linear charge density of DNA. Represent the formula for DNA containing solution. It depends of electroconductivity on temperature and cell concentration. That it also take into account what the chemical contribution from the free ions. Concentration in all three ions you can see as CS or hertz, and the concentration of the fraction of DNA molecules then remain in the form of double helix. It's also C. Okay. We have conclusions here. As a result of the experimental studies, it was shown that electrical conductivity increased parabolically as cubic root. This was shown here. The temperature depends on electrical conductivity for aqueous DNA solutions with and without it. Lithium fluid indicates melting of the DNA double helix above 47 degrees and allows calculation of the activation energy with the approximately 15 kilojoule per mole. Indeed, agreement with stability values. Comparative analysis of conductivity for solutions with and without added DNA indicates that the DNA molecule acts as a crystallization center that sequencers ions act participating in the production from the solution, and based on the obtained experimental data, a theoretical model was proposed describing the depends on the electrical conductivity and aqueous solution and temperature and concentration. Thank you for your attention.
Maria, thank you very much for your talk. I have questions about what was the chemical composition and concentration in your electrolytic solutions used for study.
So we use some stock solution of 2 mole per liter of lithium chloride, and then we mixing volumes with the ionized water. It was for our lithium solution, and then we add the for
lithium chloride. Okay, thank you very much. My colleagues, if you have any questions, Maria. Yes, thank you very much. Our next speaker will be yes, okay, from Palladium Institute of Biochemistry.
Well, then a lot of strategy, quick ones that information about this this is a multi-market studies. The cells policy position seduces one of particles actually the vote was still last dimension. And as we can see, minus is not that they have only large and relay machine expression and subs also for all as the this is conclusion. But actually, we also have some of the pages is situated as organized. Because we have just one as well as sustainable online. So this should be using operation potential and process something so as we it's very so
Dimitros, thank you very much for your very interesting, valuable talk. I have questions about the charge of the particles in this area. Do you perform the electrokinetical properties of the particles? As a second question is about what was the particle size? And third question is about the distribution of area 3, area 4 cations on the surface of the nanosphere. Thank you very much.
Thank you for the question. What about chemistry? It's actually this is a very manuscripts, which will obviously actually consider this this society. Yes, a life change. It's like the range of loans I do is Exactly. And it is how much it was shown what how many times a year. Those are two of the things. Oh yeah, yeah, yeah. And the goals. Exactly. So please question.
Colleagues, do you have any questions to Dr. Dmitrov? No, no questions. Okay. Okay, thank you very much for your the last this section we will follow your fund from the sensitization materials, yes, the presentation online. Yeah, please, Dr. Nicola, are you here?
Nikita, we can't hear you. We can see your presentation, but I can't hear you. You can turn it on your mic.
Maybe like this.
Okay, now we can hear you. Please start.
So good afternoon. My name is Mikita Lupan. I'm a PhD student at Institute for Scintillation Materials of NASA of Ukraine. And the topic of my presentation is complexes of cerium O2 nanoparticles stabilized with beta-cyclodextrin molecules that features pH-sensitive pro-oxidant properties and release and DOX release properties. And first, I would like to start from cerium oxide, pure cerium oxide nanoparticles properties. Why are they so interesting for us? Number of specific features of these nanoparticles suggests their potential use as a therapeutic agent, especially treating cancer is one of the promising directions of use of our nanoparticles. And the features that cerium possess is protective effect against reactive oxygen species, also pH-dependent redox cycling of cerium 3+, cerium 4+, which suppresses the antioxidant activity of our nanoparticles at lower pH levels, and such pH levels are commonly met in cancer cells. Also, at low pH, nanoparticles might also demonstrate pro-oxidant activities. And it was shown previously in some works that our nanoparticles of cerium oxide can neutralize the negative effects of other anti-cancer drugs. The other part of our complexes is cyclodextrin molecules. In our work, it were beta-cyclodextrin. It's a molecule that is a toroidal shape, which can form complexes with hydrophobic molecules, for example, drug molecules, and widely investigated complex is a cyclodextrin doxorubicin complex. Doxorubicin is a well-known anti-cancer drug that works in a way of incorporating into DNA chains and then damaging it with oxidative stress. And beta cyclodextrin doxorubicin complexes form quite a stable complex at the normal pH level, like 7.5. But at more acidic ones, the stability is disrupted and doxorubicin can be freed. So, and in our work, we study in complexes of these two parts, serum stabilized by the beta cyclodextrin. The first part is a characterization. On picture A, we can see TEM images, TEM image of these complexes. We can see nanoparticles. Average size was calculated to be 2.8 nanometers. XRT on picture B shows standard set of peaks of fluoride-like lattice of serum O2 and some peaks that were attributed to the cyclodextrin. At picture C, XPS measurements were obtained, and the amount of serum surplus were calculated to be estimately near 25%. And FTIR spectra shows that our nanoparticles is indeed complexes of serum O2 with beta cyclodextrin. Next, we investigated peroxidase activity of our complexes. Peroxidase activity is pro-oxidant activity in our study, and picture A, we can also the substrate that was used to measure peroxidase activity was TMB, common used sensor, and as we can see, the most intense reaction rate can be observed in the system with adding NTMB and hydrogen peroxide and our nanoparticles. At picture B, the particle concentration dependence showed, and finally the pH, the dependence of reaction rate on pH. As we can see, the peroxidase activity decreasing almost linearly from pH 4 to pH 6.5. And after pH 6.5, we can't almost see any peroxidase activity. That means that in these pH levels, our nanoparticles doesn't show any pro-oxidant activity. Also, the peroxidase activity was studied using Michaelis-Menten kinetics, widely used kinetics for enzyme-like reactions. We obtained kinetic parameters such as Michaelis constant of our nanoparticles towards TMB and towards hydrogen peroxide, and also reaction rates were obtained from these graphs. The results can be seen in this table. Also, oxidase-like activity were measured. It's an activity where we don't add hydrogen peroxide to the solution and look and studying how the TMB, the rates of TMB oxidation. All of these numbers are quite similar to the previously reported results of serum oxide, pure serum oxide nanoparticles, which indicates that our complexes still possesses the properties of pure serum oxide. Next, we studied interaction of our nanoparticles with doxorubicin. First, the DOX absorption kinetics were obtained. Picture A is an absorption at pH level 5. B is an absorption at pH level 7.4. We can see that absorption at normal pH, neutral pH levels are almost 2 times higher than at the 5 pH level. Also, pseudo-second and pseudo-first-order kinetics were used to fit the experimental data, and the pseudo-second-order kinetics were better to fit this data, meaning that process of absorption is rather chemisorption than physical absorption. Also, absorption isotherms were obtained at picture A. We used the most common models, Langmuir and Freundlich model, but they couldn't give us appropriate result. So we used SIPS model. It's a combined Langmuir-Freundlich model, and it fitted with a high R-squared parameter. That means that our nanoparticle absorption sites are heterogeneous, and that can be ascribed to beta-cyclodextrin cavities. Also, DOX release were studied. That's a DOX release graph at pH level 5 after we loaded cyclodextrin at 7 pH. And as we can see, in first 15 minutes, near 35% of DOX were released. And then a slow part started where during next 24 hours, extra 20-25% of DOX were released. We explain this phenomena with releasing DOX in first part fast release connected with beta-cyclodextrin absorption. And the slow part of this desorption is desorption from the surface of the nanoparticles. And that's a graphical representation of work of our nanoparticles. We expect, no, not expect, we saw that we can load doxorubicin at neutral pH and then release it at more acidic ones. While we can also see that nanoparticles show pro-oxidant properties at acidic pH levels, while at neutral ones, as we know, cerium oxide show antioxidant properties. That might mean that we can use this complex as an anti-cancer drug that will be more selectable towards cancer cells. The conclusions, you can see it on my screen. From your permission, I won't read it. Thank you for your attention. If you have any questions, I would like to answer it.
Could I ask from Zoom?
Excuse me, I can't hear you.
Can I ask the question from Zoom?
Yeah, of course.
Yeah. So thank you so much for your nice presentation and congratulations for your nice work, first of all. For me, it was interesting to know how you characterize DOX complexation, this point, because it can be also just mixture and you have after release of DOX during the time. If you're sure that you have complex with your nanoparticles. Or it's just a mixture?
No, it's not a mixture. We have
Because
Okay,
with XPS,
Yes,
what
yes.
I understand, you characterize your nanoparticles, that you have cerium oxide in the core, in the shelf you have polymer part, cyclodextran part, if I understand well. Because XPS, you characterize surface of cerium oxide.
Yeah.
Yeah, but it's okay. Probably it's
In the, I'm not quite familiar with the synthesis methods, but as I know, cyclodextrin was used as a stabilizer of our nanoparticles, and I think that if it wasn't incorporated to the surface of nanoparticles, they wouldn't, no, they would be much bigger.
But if they stabilize, which mechanism of stabilization, we have such question as well. So, but it's okay. If you have some reference, according that you have complex with doxorubicin, for example, you should put in your presentation, but think about how it's possible to characterize that you really have complex with doxorubicin.
Yes, thank you.
Okay, thank you so much one more time.
Thank you. Maybe questions from conference hall. Yes, we have one question from conference hall.
Please explain us why you have chosen exactly cyclodextrins and not other organic microcycles to form nanoparticles with cerium oxide. So why just cyclodextrin, not other organic macrocycles?
Yeah, as was previously said, the cyclodextrin were previously studied its interaction with doxorubicin, and it's have quite an interesting pH dependency of stability of these complexes that help release release doxorubicin exactly at slightly acidic pH values, and that's why we used cyclodextrin in this one.
Thank you for your presentation and interesting discussion. And now we go to the next section nano-optics and photonics. And the first speaker in this section, Dr. Oleg Dmitriev from Bashkirov Institute of Semiconductor Physics for the National Academy of Sciences of Ukraine.
Hello, can you hear me?
Hello, yes.
Okay, so let me share my screen. Can you see my screen?
Yes, it's okay. You can start your presentation.
Okay, good afternoon to everybody. I would like to present results devoted to the management of emission of perovskite and carbon nanoparticles by surface modification with specific molecules which possess thermally activated delayed fluorescence. This work was realized in collaboration of three institutions: Kyiv University, Kyiv National University, Kaunas University of Technology, and the Institute of Semiconductor Physics. So first of all, let me remind the importance of surface modification of nanocrystals and quantum dots, because surface quality of nanoparticles is crucial for their physical and chemical properties, because surface engineering of quantum dots improve their performance and stability in various media. This enhance optical and electronic properties, surface passivate surface defects, reduce non-radiative recombination, and enhance photoluminescence, which is important in this work. Also, surface engineering is important for controlling dispersibility of nanoparticles in different solvents, tailor chemical reactivity of nanoparticles, and also is crucial for improving the performance of nanoparticles in solar cells, light emitting diodes, and photodetectors. But usually, surface passivation is realized by application of conventional shells, which are normally optically passive. And in this work, our target will be to use optically active shells in order to deliver potent-induced charge to the nanoparticle surface, and in this way to influence photoexcitation and photoluminescence of specific nanoparticles. This is important particularly for development of nanoscale photovoltaics. So here you can see this example of nanoscale photovoltaics when nanoactive quantum dots are combined with organic molecules, which after photoexcitation deliver charge to the nanoparticle core, and in this way the charge separation occurs between organic molecule and nanoparticle core. In this work, we used specific nanoparticles that is carbon nanodots, which consist of the graphitic crystalline core, and but have rather rich surface, which can contain different moieties like carboxylic groups, like amino groups, and in our case, these nanoparticles also contain fluorine atoms. And on the other hand, we used also perovskite nanoparticles, which are very active now in development of solar cells and organic light emitting diodes. And these nanoparticles are commercial. They were bought from Sigma Aldrich, and they are stabilized by oleic acid and oleiamine molecules. But as I will show you, nevertheless, the interaction with other molecules is also possible. On the bottom of this slide, you can see the typical absorption and emission spectra of these nanoparticles, which emit light in the visible near 500 nanometers for carbon nanodots and near 450 nanometers for perovskite nanoparticles. On the other hand, we use the organic molecules, which possess a thermally activated delayed fluorescence. And these molecules have specific structure because they consist of the donor and acceptor part. And we use the two groups of molecules which have carbonyl moiety in the acceptor part and the nitrile group in the acceptor part. A specific of these molecules which possess thermally activated delayed fluorescence is that upon photoexcitation, they provide a charge transfer from the donor part to the acceptor part, which is accompanied by molecular twisting when acceptor group rotate in respect to the donor group for specific angle, which is close to the 90 degrees. and which provide a good separation of the electron and hole on the acceptor and the donor part of the molecule. And also, these molecules are interesting because they are used in organic light emitting diodes of the third generation. And on the left side, I can briefly describe the energy scheme, how it is realized. So this molecule has singlet and triplet energy levels, and of course, a singlet level provides fluorescence, but triplet energy level, in principle, it can provide phosphorescence, but the phosphorescence is not effective because it is normally quenched at room temperature. But in these materials, there is also the charge transfer singlet level, which is very close to the triplet one, which is separated by energy comparable with room temperature energy. That means that the electron which sit on the triplet level can be easily lifted by a reverse intersystem crossing to the singlet charge transfer energy level, from which it can produce photoluminescence, which with delayed time. So this provides a very effective work of these molecules in the light emission diodes, because almost all excited electrons contribute to the emission. For us, it is important that during excitation of these molecules, they have a charge transfer from the donor to the acceptor group. But this process can proceed by immediately. When we excite the molecule, charge can go immediately from the donor to the acceptor, or first it can be excited at the donor part, then molecule become twisted, and after the twisting process, the excited charge can transfer from the donor to the acceptor part. These are a little bit different processes, but they are important because they contribute differently to the effect of the photoluminescence of nanoparticles, which I will show later in this work. So let's start with carbon nanoparticles. Interaction of different molecules which possess thermally activated delayed fluorescence with carbon nanoparticles. And first example is this molecule, CMP. So this molecule has a charge transfer absorption band shown here near 420 nanometers. And when we add this molecule to the dispersion of carbon nanoparticles, absorption spectra of these nanoparticles is shown here by black line, we can see that charge transfer emission becomes suppressed of this nanoparticle, shown by dotted line. At different dye concentration, we have a similar effect. And also, we have separation of a charge transfer emission of this dye in the presence of carbon nanoparticles. And on the other hand, we also have separation of photoluminescence of carbon nanoparticles itself. When we add dye, when we increase concentration of dye, shown here by dotted line, we observe gradual decrease of photoluminescence of carbon nanoparticles as well. Also, the other effect is the blue shift of charge transfer emission of CNP in the presence of carbon nanoparticles. So we can conclude that interaction of these molecules with the surface of carbon nanoparticles result in a mutual dumping of both dye and carbon nanoparticle emission. maybe which is not good for potential application. But I would like to note that these molecules possess very strong charge transfer absorption. And this charge transfer absorption correlates well with suppression of emission of carbon nanoparticles. The other dyes with neutral groups also show suppression of emission of carbon nanoparticles, and also carbon nanoparticles also suppress the charge transfer emission of these dyes, shown here in this spectra. The other molecules which possess carboxyl group in the acceptor part also produce a similar effect. That means that they suppress photoluminescence of carbon nanoparticles very strongly, and also carbon nanoparticles suppress charge transfer emission of this molecule as well. The other example concerns perovskite quantum dots. This is a more interesting example. So again, we used different molecules with with carboxyl and nitrile groups. And first example concerns again this molecule ACCNP. What we can see that when we add this molecule to the dispersion of perovskite quantum dots, we can observe suppression of photoluminescence of perovskite quantum dots. You can see here with a different concentration, a small concentration of dye, and this concentration was increased by a factor of 4. We see more impressive suppression of emission of quantum dots, but simultaneously we can observe a suppression of charge transfer emission of dye itself. If we look at charge transfer absorption of the dye, we can see that the charge transfer band become more narrow and redshifted in the presence of carbon nanoparticles. The other dyes show the different effect. These dyes shown here, they possess a very small charge transfer absorption, and they produce a very small influence on the photoluminescence of perovskite quantum dots. So we can see that emission almost does not change, and in principle it represents the superposition of the emission of quantum dots and the dye molecule. And the other group of molecules which has very small charge transfer absorption, or even we cannot observe the charge transfer absorption of this molecule in the absorption spectra. And these molecules produce enhancement of quantum dot emission by by 16% in this case, and by 48% in this case, which is very interesting. And again, this correlates with the charge transfer absorption band, which is not observed here. If you remember, dye with the strong charge transfer absorption suppresses the photoluminescence of perovskite quantum dots. But in this case, when we do not have charge transfer band in the absorption spectra, we observe just the very good enhancement of photoluminescence of perovskite nanoparticles. So the case of molecules with carboxyl groups produces enhancement of photoluminescence of perovskite nanoparticles. And especially interesting is the case of benzophenone molecule, which is a small molecule, but which produces very high enhancement by almost a factor of 2 of photoluminescence of perovskite quantum dots. Here you can see the absorption of benzophenone, which starts from approximately 380 nanometers. And but enhancement is independent on the excitation wavelengths. For example, when we excite at 365 and at 405 nanometers, we still observe the enhancement of photoluminescence. That means that the mechanism of this enhancement is not due to the energy transfer, but due to the specific interaction of this carboxyl group with the surface of perovskite nanoparticle. And in order to analyze the mechanism from the chemical point of view, we should consider the surface of perovskite nanoparticles, which contain trapping sites, normally due to the uncoordinated lead ions, which produce suppression of photoluminescence, this quantum dots. And if we passivate these lead ions with Lewis bases, then we can improve the photoluminescence, and we can consider these molecules from the point of view of Lewis basicity. For example, this molecule with pyridine acceptor group has very good Lewis base properties. This molecule has less basic properties, and benzophenone also acts as a Lewis base. And we can see the correlation between Lewis base strengths and enhancement of photoluminescence of perovskite nanoparticles. That means that just passivation with Lewis bases produces enhancement of photoluminescence of perovskite nanoparticles. So, in conclusion, I would like to remind that molecules which possess thermal activated delayed fluorescence with different acceptor groups render different effects on photoluminescence of perovskite and carbon nanoparticles. I showed that practically all molecules quench photoluminescence of carbon nanoparticles and vice versa. But dyes with neutral groups and strong charge transfer absorption quench photoluminescence of perovskite nanoparticles, but dyes which has very weak charge transfer absorption can enhance photoluminescence of perovskite nanoparticles. And the mechanism of photoluminescence enhancement is suggested due to the surface passivation using Lewis bases that screen charge trapping sites. I would like to thank our funding bodies, and of course, I would like to thank the Ukrainian Army for possibility of this conference, and thank you for your attention.
Thank you for your presentation. Questions? If we have no questions, thank you again for your interesting presentation.
Oh, sorry, can I put question?
Yes, okay. One small question. We have no time.
There is a question. What is the method of obtaining for fabrication carbon nanoparticles? Carbon nanoparticle was used by you.
Method of synthesis of carbon nanoparticles. So I'm sorry, I did not have time for description, but this was performed in Kiev University by specific method, which is very long to describe because there are many components which were added to the mixture, and this component were heated up to specific temperature and then cooled down, and so this is a very complex process. I cannot describe it in a few minutes.
Thank you very much. Thank you.
Thank you for your question, and thank you again for your presentation. And the next speaker, Dr. Alexey Kapitanchuk from Bogolyubov Institute for Theoretical Physics of the NASA of Ukraine.
Hear me? Good afternoon.
Yes. Good afternoon.
I'm trying to share my presentation. Can you see my presentation in full screen?
Yes, it's okay. You can start your presentation.
Thank you. Once more, good afternoon, dear colleagues. I'm glad to present the result of our theoretical work, which was carried out at the Boголюбов Institute for Theoretical Physics, NASA of Ukraine, in Department of Theory of Quantum Processes in Nanosystem, and was co-authored with my colleagues, Professor Elmar Petrov and Dr. Evgen Shevchenko. And this work concern the phenomenon of electrofluorochromism, when the color of the luminescence of materials depends on the parameters of external electric field, and in which fluorescence is usually turned on, off, or switched between different colors under the influence of electric stimulus. Typically, fluorochromic properties are exhibited by diodes, fluorophores, some polymers, and the mechanisms of changing the color of the emission are of considerable interest from both fundamental and practical points of view. Among optically active fluorophores that are able to absorb or emit light, a wide class of substances with active delocalized pi orbitals is distinguished. For example, zinc phthalocyanine molecule, which are delocalized by which are characterized by two delocalized pi orbitals. Recent experiments using STM techniques on single molecules have shown that the states of the molecule act not only as a mediator in the formation of current, but are also responsible for electroluminescence in two ranges, depending on the polarity of the field applied to the two contacts that are STM tip and metallic substrate. The experimental scheme is presented on this figure. Another feature of this fluorophore is that both neutral and charged cationic states of the molecule participate in the optoelectronic process, which is observed in experiment as two different emission lines for positive and negative applied voltage. The dielectric layer provides a separation of the molecule from the metallic substrate, preventing modification of the electronic states of the molecule, which correspond to the states of the molecules in the gas phase. The aim of our work is to propose a physical mechanism that explains the features of the behavior of STM-induced electroluminescence in single molecule contact, taking into account both the neutral and charged states of the molecule. In our model, in our theoretical approach, we consider a system with two electrodes, STM tip and substrate, and a molecule is placed between them. Due to a weak coupling between the molecule and these electrodes, Hamiltonian of the such system in the absence of magnetic field can be represented as sum of three components, which are described by formula that includes Hamiltonian of electrodes, Hamiltonian of molecule, and the last component describes an interaction between the molecule and the electrodes that is characterized by coupling beta. Operators A and C define the one electron creation and annihilation in the conduction band of electrodes and molecules correspondingly. Electron tunneling between the tip and the isolated metal contact is mediated by the molecule, which can change its electronic state both in neutral or charged form. When the states are changed, it is accompanied by the filling of the frontime molecular orbital. The figure shows the electronic configurations for those electronic states of the molecule that participate in the optoelectronic process. So we consider here 6 states in 2 bases: 1 electron p orbital basis and molecular orbital basis. These states are presented in schema and correspond to ground and excited states of neutral and charged molecules. The states reflect the filling with electron of 2 frontile pi orbitals. The filling process is controlled by a voltage bias via the shift of energies of molecular orbitals which respect to the Fermi level of both electrodes. Experimentally, the STM-induced electroluminescence occurs at a weak interaction of the molecule with the electrodes. We show that at such condition, the steady-state current through the electrodes and the integral intensities of electroluminescence lines, the frequency of transitions in neutral molecule and its cationic form are given by the expressions. Each current component related to sequential, elastic, inelastic roads of electrotunneling, as well as intensities of emission lines are proportional to the stationary occupancies P. The magnitude of the latter depend on the kinetic processes in the junction, which are controlled by the voltage bias. Associating the molecular junction with the open quantum system, we adopted the methods of non-equilibrium statistical mechanics to obtain expression for the current and intensities for emission lines. We show that the temporal behavior of occupancies P of molecular states and the current can be evaluated from the equations, where non-equilibrium density matrix of entire system evolves in time according to the Liouville equation. Here, H is discussed about Hamiltonian of the entire system. G is the relaxation matrix, the elements of which are responsible for establishment of equilibrium Fermi distribution in the electrodes and Boltzmann distribution in the vibrational bass. Having hence analytical expression for the steady state frequencies, for the steady state current and intensity of emission lines, we solve the corresponding equations at time that is significantly exceeds the characteristic time of the establishment of steady state regime of the electronic transmission within the system. To obtain the analytical result, we use the following type engine model for the molecule. Corresponding Hamiltonian. Thus, we get the molecular energy of 2 singlet states and 1 3-fold degenerate triplet state of neutral molecule, as well as 2-fold degenerate state of the anion and 2-fold degenerate states of ground state and excited states of the cation. Molecular energies are expressed via pi orbitals energy as well as Coulomb and exchange interactions between different orbitals and on-site interaction. That is expressions. The theory has been applied to explain the features of low-depth frontier STM-induced electroluminescence in the fluorophore placed on the salt layer of insulator. Schematic, this device schematic presented on this figure. We show that the features of an optoelectronic process are associated with the change of the voltages defined by the formula and are expressed through the basic transmission gap. delta E, that characterizes the energy differences between the energies of charge and neutral states of the molecule in the junction when an electron arrives at the Fermi level or departure from the electrode. Critical voltages demonstrate at what bias voltages the occupancy of states and the current voltage characteristics of molecular junction can change the magnitude. This graph shows an example of the stepwise behavior of the population values of the 6 kinetic states and the current value by components depending on the values of the applied voltage. It is clearly seen two significant steps on both panels in the graph at negative and positive value of the bias voltage. These values can be associated with the experimental values of 1.9 volts and minus 2.2 volts. So we can substitute the expressions for the critical voltages and taking into account the values of the radiation energy as well as experimentally known values of the electronic gap. We were able to estimate fundamental transmission gaps in the molecular junction. So the fundamental transmission gaps, like the energies of singlet and triplet states, as well as ionization potential and electronic affinity, in the table. And show how the values of corresponding energies in real molecular junctions differ from those for a gas phase. The insulator layers effect on the energy of anion much more strongly than on cation. The quantum mechanical calculations were performed for phthalocyanine molecule at DFT level, and the shapes and energies of frontier molecular orbital are presented in the figure at the bottom of this slide. Molecular energies are obtained through the frontier orbitals, HOMO-LUMO, as well as the parameters of Coulomb and exchange interaction between pi electrons is in molecular junction. The presented schema reveals a fundamentally important result, indicating the possibility to obtain real values of the energies of the frontier orbital of the fluorophore under real experimental condition. Two optical energies are associated with observed electroluminescence lines mentioned above. HOMO and LUMO energies are expressed via energy of pi orbitals and interaction between them by following equation. Expression for the intensity of emission line shows that the intensity dependence of the voltage bias via the state occupancies of excited state of neutral and positively charged molecule. The table shows analytically how the relative light emission line exhibit a stepwise change in their intensity near the values of critical voltages. The results are presented for cases where the plasmonic response changes or does not change the optoelectronic processes. Due to lack of time, we discuss here the experimental results for the case when optical transition in the molecule junctions occur against the background of weak plasmonic response, so that the rates of such response are much smaller than the charging rates, which means that the charging kinetic is mainly controlled by an electron tunneling between the molecule and the tip rate, gamma 1, and between the molecule and the isolated metal rate gamma 2. Due to this isolation, the gamma 1 exceeds strongly the gamma 2. Then if the absolute values of the bias voltage is below of corresponding value of critical stresses, there is no light emission. In the opposite case, the line X0 has a weak intensity in both polarities, whereas the line X plus exhibits a good intensities only at negative polarity. Kinetic theory allows us to give a physical understanding of the results presented in the previous slide using following scheme. The presented scheme shows that the controlling role of two main factors that determine the picture of electroluminescence around the two values of critical voltages. Each of the diagram correspond to a certain voltage range, which is present here, the bottom part of each diagram. The first control factor is the stark shift of both the energy levels of the charged molecule and the chemical potential of the tip and metal contact respectively. At critical voltages and stark shift lead to a resonant popping of electrons between the molecule and electrode. The second factor is the ratio of changing rates, gamma 1, 2. In the experiment, the rate gamma 1, shown by solid arrows in the scheme, greatly exceeds the rate gamma 2 marked by dashed arrows on the diagram. On this diagram, in the case of positive polarity of bias voltage according to the position of energy level, in the system only the ground state of a molecule is populated. So other hypotheses are zero. There is no electroluminescence in this case, but in this due to formation of cation and excited singlet state of the molecule can be realized that lead to detect a very weak X0 emission line in the experiment for this scheme. For negative polarity, emission is detected in right case only. Now, the probability of realization of an excited cation significantly exceeds the similar probability for an excited singlet. Therefore, in the experiment with negative polarity, the emission line X plus has a much more intense than line X0. Thus, we were able to explain the effect of electrofluorochromatics discovered in recent experiments. Summarizing a kinetic model of the optoelectronic process in a molecular junction has been developed where the electronic and optical properties of the junction are controlled by the filling of the frontier orbitals of the fluorophore with electrons. Due to lack of time, I will not repeat the main result listed here since most of them were discussed during my presentation. The results are partially published in our paper. The reference is below. Finally, the authors of this work acknowledge their support by the National Science of Ukraine and Simons Foundation USA. And thank you very much for your attention. I will be happy to answer your question.
Thank you for your presentation. Any questions? No questions. Thank you again for your interesting presentation.
Thank you.
And the next speaker, PhD student Serhiy Polyboroda from Lviv Polytechnic National University.
Hi, can you see my presentation? Can you see my presentation? Can you hear me?
Yes,
Okay,
it's
good.
okay. You can start your presentation.
Okay. So my name is Serhiy Polyboroda, and today the topic of my presentation is a sensor for measuring the refractive index of liquids and gases based on Fabry-Perot interferometer. Sorry. As you can see, figure 1 shows the structure of a Fabry-Perot interferometer with interference mirror, where reflectance of such mirrors can exceed 0.999. We'll first consider a simplified model of the Fabry-Perot interferometer, which is widely described in the literature. The simplified model allows us to study the main characteristics of such interferometer. So from previous figure 1, it shows, here it is again, multi-layer structure of interference mirror, where D is the distance between the mirrors, what is distance between the mirrors and the angle at which the light beam propagates the medium under study. It's a simplified model interferometer. It is assumed that the mirrors are very thin and the reflection coefficient in intensity in the absence of a second mirror is equal R. And here you can see the formula for the transmittance T of the Fabry-Perot interferometer. This is formula 1. Going further from formula 1 for transmittance equal 1, we can get formula 2. For order of the interference and P. On the basis of formula 2, it is possible to find the formula for thickness dm, at which, depending on other parameters, the transmittance of the interferometer equals 1. On formula 4, as you can see, we have a formula for the sharpness of bands F. And also from formula 2, we can determine the spectral sensitivity by taking the complete differential of the left side and equating it to 0. Therefore, we can find the spectral sensitivity and the half-width transmission of the spectrum in formula 6. Now taking into account that half-width of the transmission spectrum is smaller than wavelength of light, we can find formula 7 for the half-width of the transmission spectrum. And we can determine the quality of the sensor in formula 8. And next we can find the angular sensitivity. Angular half-width transmission, and we can find the angular quality of the sensor, which is close to just sensor quality, so we can presume that the sensor quality is equal to angle quality. And following the numerical analysis, numerical analysis of the Fabry-Perot interferometer was conducted using the matrix method for the wavelengths close to 632.8 nanometers, and for 4 light propagation angles 0, 5, 10, and 15 degrees. The refractive index of the liquid was 1.3317. And the refractive index for the substrate CO2 was 1.457. Each interference mirror consists of 5 pairs of layers. High refractive index
2.5837 for CO2, and a low refractive index for magniferum. Layers thickness were determined by the next formula, and all the calculations were done for m equals to m is some integer. So the thickness D for the simplified model of the interferometer were determined by the formula 3, as shown before, for m equals 10, and for the interferometer with mirrors were determined by the condition of achieving transmittance T equals 1. The thickness are given in column C of table 1, which I will show you on the next slide. Reflection coefficient of the interference mirror was calculated respectively for 5 pairs of layers that were surrounded by media with refractive index of 1.457 and 1.3317 respectively. This reflection coefficient was also used for calculation of simplified model of the Fabry-Perot interferometer, and it's slightly dependent on the angle of propagation of the light beam and the medium under study. During the numerical analysis of an interferometer with interference mirror, we have the next formulas for spectral and angular sensitivity, respectively. In our numerical analysis for the calculation by formula 13, the refractive index equals 0.0001. The result of the calculation of spectral sensitivity are given in column 6, which I will show you in the next slide, and the angular sensitivity in column 9 of table 1. This sensitivities for simplified interferometer model were determined by formula 5, which was shown before, and 9, and for interferometer with interference mirror by formula 13. As you can see, the sensitivity for both interferometers are slightly different from each other. For interferometer with mirror, the sensitivity is lower compared to the simplified model. Here we have figure 2 that shows the spectral and angular dependency for transmissions of the interferometer with interference mirror. And here we have table 1. So for rows from 2 to 5, I can probably pay it from 2 to 5, we have a simplified model. And from 6 to 9, we have a real interferometer. Oh, sorry. So now we have figure 3 that shows the resonant wavelengths and resonant angles for transmittance equals 1, depending on the change in the refractive index and of the liquid under study. Figure 3 resonant wavelengths and resonant angles for T equals 1, depending on the change of the refractive index 1 of the liquid under study. The data in Fig 3a are calculated at the angle 10 and determined at 633.8 nanometers. Blue dots, as you can see here, are the result of the calculations. The green curve is drawn through the dots. The red straight line connects the point with refractive index plus minus 0.01. As we can see, the spectral dependence in the straight line is that spectral sensitivity is constant over a wide range of changes that is positive n. At the same time, the angular dependence is somewhat nonlinear. This curse of dependencies can be explained by formula 5 and 9 that was shown before, and we will get to table 2 that summarize parameters of sensors. So from this table 2, we can see that sensitivity as theta of Fabry-Perot interferometer is the best in a matter of angular quality and quality overall. And in conclusion, a comparison of 4 types of sensors shows some advantages of the sensor based on the Fabry-Perot interferometer. In it, you can quite easily adjust the spectral and angular resolutions as well as the quality of the sensor by changing order of interference, the sharpness of the band F at the same time without changing the sensitivity. Spectral sensitivity can be increased by wavelengths of angular sensitivity, and it can be changed by the angle of propagation of the light beam in the medium understanding. The sensor is better in quality than the sensor based on a prism structure and based on a metal lattice. The principle of operation of which is based on the resonance of surface plasmon polariton waves. A sensor based on a Fabry-Perot interferometer can have a higher angular sensitivity than the other sensors by selecting the angle of propagation of the light beam, but a lower spectral sensitivity than sensor based on the resonance of the surface plasmon polariton waves. Sensor based on the resonance of waveguide modes on the electric gratic is inferior in the sensitivity to a sensor based on interferometer, although it may have better quality. However, it should be noted that the sensor with the quality of 17,170 are practically impossible to manufacture. That's all. Thank you for your attention.
Thank you for your presentation. Any questions? One question in conference call.
Thank you. How large could be the distance between neurons during interferometer? I'm wondering because if it is too small, the microns, several microns, could be a problem with feeling. It's uniform feeling. Sorry, can you hear me?
Hardly, if truth be told.
I'll try to repeat. How large is the distance between mirror in your sensor?
I think that was supposed to be mentioned, but let me check. I think question was about the distance between mirrors at the beginning. So the distance between the mirror is the angle at which the light beam propagates in the medium under study. If I correctly hear the question, sorry, problems with internet connection on someone's side, maybe on mine.
Yes, exactly. What's the number? Value.
I will probably refer to my colleague Володимир Михайлович, яка там була дистанція між дзеркалами? Володимир Михайлович, ви тут? Yeah, sorry, I wanted to ask my colleague to be certain, but since he's not...
Мікрофон. Десь більше одного мікрона. Ну, кілька мікрон було.
So the distance was more than 1 micron. That's the answer for the questions. And thanks once again to the speaker. And we will move forward to the next presentation. That will be done by PhD student Maxim Angelov. So sorry, the wrong list. PhD student Artem Podshebiakin from Taras Shevchenko National University of Kyiv, Ukraine.
Hello, can you hear me?
Yes, I can hear you. Please share your screen.
Yes. Is it okay?
Yes, but not in full screen mode. You can click the button on the top of the screen. Yes, that's this button.
Okay, let's start.
Yes.
Good afternoon. Today I will present my work about lasing in tight mesostructured organic inorganic nanoscale films in the subtrical region. Our research aim is to develop planar waveguide laser of minimal size for integrated optoelectronics. It can be combined with components like transmission lines, modulators, filters on a single chip. However, the conventional rare earth doped solid-state planar waveguides are not suitable for this work, so I present die-doped gibrid film on TH2 and CH2 matrix. Motivation. Why tin die-doped film? First, it's miniature size to strong gain medium that will work when the film thickness is reduced. We can also work with polymers, but they dissolve dyes at high concentration, and they often suffer from luminescence quenching, and typically have lower refractive index than substrate, glass substrate. To solve this, we used sol gel technique to synthesize our gibrid tin films. Here we can see the structure of the film and the glass substrate. We fabricated mesostructured hybrids with TH2 and CH2 matrices, but in our work we have our main study with TH2 matrices because they have provided better refractive indexes near 1, 5, 6, and 5 value. Nanopores filled with molecular solutions of rhodamine 6G with nanoporous network on all surface of the film. Two sample types were made with thick of 330 nanometers. It's have about cutoff thickness with true electromagnetic waveguide modes. And second thick film with 200 nanometers, it have below cutoff critical value for waveguide mode of radiation. So we have used for this radiation name quasi-waveguide regime. About fabrication. For films, we have used two technologies, spin coating. It's for creating thin and uniform layers with thickness inversely proportional to the square root of to the spin speed, and deep coating, better for thickness proportional. And our and our technology have said that we have a lot of films about from thickness one, not thickness, with refractive index from 1,499 and to 168 indexes. About a waveguide principle. Waveguide confidence depends on two bases. The total internal reflection occurs if the film refractive index is larger than both substrate and air. We have around 1.565 when substrate have 1.52 and air near 1. And dispersion equation condition defines which film thickness support guided modes. When the thickness is the cutoff, it's our 340 nanometers film. The waveguide supports true guided modes with minimal losses. If when we use a second with reduced below the cutoff, total internal reflection fails and the light leaks into the structure into the substrate. But however, due to high dye concentration that provided us enough optical gain to compensate for leaking losses, we we looked at also emission from the substrate. It's our schematic experimental setup. Pumping was done with the second harmonic off-cue switched anti-yacht laser at 532 nanometers with pulse duration 15 nanoseconds. And the pump was focused into the track on the film about 3.05 square millimeters using cylindrical lattices. Emission was recorded using a diffraction spectrograph with CCD camera. So, about emission features. The films showed us sharp spectral narrowing at the threshold, typical of lasing, with line with below 5 nanometers. In TH2-based films, the lasing threshold was at near 0.14 megawatts for squared centimeter for 340 thickness film, and near 0.65 megawatts for 200 nanometers subcritical film. In CH2 film, there was about an higher an order of magnitude higher due to lower refractive index. Film emission was dominated by quasi-waveguide mode reflected inside the film walls, and the substrate emission were formed by luminar interference leaking into the substrate. Also, we studied influence of immersion. Emission by placing a simple quartz plate thickness by 5 millimeter with a glycerin layer on the free substrate surface with a pressed back reflection. Under this condition, emission was concentrated almost entirely in the film itself. This demonstrates us that subcritical films can act also as lasers. More about our two emission modes. Emission from the film and diverge strongly due to diffraction from the small aperture, and the emission from substrate and diverge less, or as it originated from a larger aperture. Both showed us narrowing with pump intensity through lateral emission remained broader, resembling amplified spontaneous emission. The thicker films showed us interference fringes at angular divergence of 6 of value 6 inch, evidence as coherent waveguide lasing. So our main reasons. We used a Solgel method to synthesize two gibrid mesostructured TH2 films with 340 and 200 nanometers thickness. The films had nanopores of value 12 nanometers, which prevented us dye aggregation and avoided us luminescence quenching. Observing us give the result of 0.40 megawatts for square centimeters. That is good value. We speculated waveguide and quasi-waveguide modes. Also, we studied about theory of their where they originated from substrate, from film. We gave emission detected from the both films and substrate ends. And we demonstrated that laser action is possible even when we have a thickness value of film below of a critical value, thanks to immersion and luminescent gain. That is confirms that resonator-free lasing is possible and can be provided on single chip in future. In future, we will try to reproduce the results with new films. It's very painful moment because we lack of a lot of films in our work. We also want to try test hybrid films with polymer-only films to try to compare the results. And also we want to explore advanced multi-layer architectures to control spectra and reduce the results to below maybe 0.005 megawatts. Conclusions. We demonstrated that giblet polymer interacting fins doped with rhodopsin 6G can lace even at subcritical thickness. Both waveguide and quasi-waveguide modes were observed, depending on thickness and refractive index. Internal reflectors and substrate modes act as feedback, making external resonators unnecessary. And this work points to development of our work to make complex low threshold integrated laser sources for photonics and integrated optoelectronics. Thanks for your attention.
Thank you for your presentation. Questions? No question. Thank you again for your interesting presentation. And it was the last presentation in the morning session. Now we have time for lunch. And the next session will be started at 2 p.m. Thank you.
Hello, dear colleagues. Once again, we return back from the lunch break. And we will start our next session, nanoplasmonics and surface-enhanced spectroscopy. I will be the chairman of this section. My name is Andrei Yaremkevich, and the first speaker from the section is PhD student Maxim Sobolevsky from the Institute of Molecular Biology and Genetics of NASA of Ukraine. Maxim, can you hear us?
Good afternoon, dear colleagues. Yes, I can hear you.
Okay, so please share your screen with us and you can start.
Can you see the presentation?
Yes, we can see your presentation. Please start.
Thank you. Let me introduce you to the work of our laboratory on the topic of electrospherical stabilization of citrate-bound gold nanoparticles for signal enhancement of hybridization DNA biosensor. For those of you who are unfamiliar with the topic, let me brief you on the SPR spectrometry. This is a method of analysis of biofluids by biosensor means. Surface plasmon resonance spectrometry is employed to detect molecules that are absorbed on the sensitive gold layer. And this physical effect is used in SPR biosensors, particularly DNA hybridization biosensors, to monitor affinity interactions between biomolecules. In other words, if we detect an interaction between two molecules, between two, for example, DNA strands on the surface of an SPR biosensor, we see a shift in the biosensor signal. Unfortunately, in most SPR biosensors, the detection limit of such measurement is too high to detect the physiological concentrations of DNA markers. For example, markers of chronic myelogenous leukemia, the oligonucleotides of BCR-ABL hybrid gene, which are present in our blood in the form of circulating tumor DNA in concentrations up to attomolar concentrations. To enhance the analytical characteristics of our biosensors, we develop biomodified gold nanoparticles, which are used to enhance the signal of mass-sensitive SPR spectrometer in sandwich format, as you can see on the figure 4. When our biosensor system detects interactions between target oligonucleotide, which is painted in red, and two probe oligonucleotides, we see it as a drastic shift in SPR spectrometer signal. These gold nanoparticles are synthesized by us in our laboratory by the method we developed ourselves and then modified with thiolated biomolecules and stabilizing ligands. Here you can see two different configurations of surface layer of such nanoparticles. On the left, you can see our prior nanoparticle design. In our previous work, we used probe DNA labeled SHDP, detection probe, and SH means thiol group, which is used to establish a stable covalent bond between a biomolecule and a nanoparticle surface. and other thiolated molecules, lipoic acid, La, and MCH, are then used to electrosterically stabilize these nanoparticles. Electrosterical stabilization of nanoparticles is a promising topic in nanophysics, in nanotechnology, which allows to produce especially stable nanoparticles, which are shielded from interactions with other nanoparticles and other surfaces by a combination of steric and electrostatic factors. You can see here that MCH is a non-polar, is a non-charged molecule without any charges, and LA lipoic acid bears a negative charge, which helps to shield these nanoparticles from other nanoparticles and maintain its colloidal stability. On the right, however, you can see a newly developed nanoparticle. On the basis of our previous work, we decided to substitute lipoic acid with an equivalent amount of oligonucleotides. We added more oligonucleotides, more probes used in our sensitive detection of DNA targets, and developed gold nanoparticles that are modified only with oligonucleotides, with probe oligonucleotides HDP and mercaptohexanol, which blocks an occupied surface of gold nanoparticles and generates steric hindrances. DNA is by itself a charged molecule which generates electrostatic barrier for interaction between different nanoparticles and helps reduce the aggregation. The aggregation of nanoparticles presents itself even on the stage of synthesis of gold nanoparticles. This synthesis is very simple. It can be achieved only with magnetic stirrer, with heating and fume hood. The most crucial step of this synthesis is its timely stop, which ideally takes place when the color of gold nanoparticle colloid during synthesis changes from dark purple to faint red, which you can hopefully see on the third picture. When such nanoparticles are boiled extensively, when we boil them for a long time, it results in temperature-induced aggregation of gold nanoparticles. So, to modify these nanoparticles to achieve the most reproducible results, we monitor our nanoparticles after synthesis and choose for further modification with biomolecules only those nanoparticles that have a range of diameters between 8 and 28 nanometers. This both achieves the biosafety of our nanoparticles, since small nanoparticles with diameters less than 4 nanometers have cytotoxic and genotoxic properties, and allows us to access the highest possible surface area of nanoparticles, since the less the diameter of nanoparticles in our solution that were synthesized from the same number of atoms, the higher the surface area of such nanoparticles. The results of application of such nanoparticles to our biosensor system are presented on this slide. Here you can see the non-specific responses of our biosensor to injection of such gold nanoparticles, which are ideally the less the better. And you can compare the responses of the biosensor to prior nanoparticles and newly developed nanoparticles, which are modified with high number of oligonucleotides. This lowering of non-specific biosensor signal also is beneficial in the fact that the biosensor is easily regenerated after such an experiment. Since biosensors are by definition devices that can be used many times over, our goal in our work is to develop such gold nanoparticles that will be such nanoparticles that will cause the lowest non-specific signal, and after this experiment, that can be washed the most effectively from our biosensor sensitive surface. And the specific signal of our biosensor is presented on this slide. Here you can see the injection of target oligonucleotides and further injection of gold nanoparticles that are modified, forgive me my mistake, they are modified only with probe oligonucleotides, SIH-DP, and mercaptohexanol. And here you can see that compared to the previous slide, compared to the non-specific signal of our biosensor, this specific signal is more than 3 times higher than the non-specific signal. The conclusions of this presentation were voiced previously, and thank you for your attention.
Thank you very much for your presentation. Do we have a question in the hall? I have one question. Oh, yes, Oksana Krupka has a question.
I have question. First of all, thank you for your nice talk and for nice presentation. Do you have some idea about citrate? If you still have citrate on the surface of your nanoparticles or not?
Thank you for your question. It is it is hard to assess the exact composition of the surface layer of nanoparticles. Although in the case of citrate, which blocks the surface of such nanoparticles immediately after their synthesis, it can be said that our modified nanoparticles with oligonucleotides, with mercaptohexanol, do not contain a traceable amount of trisodium citrate on their surfaces, since such molecules, citrate ions, are weakly bound to the gold surface only by electrostatic interactions. Such electrostatic interactions can be nullified when we introduce such gold nanoparticles into the medium with high concentrations of positively charged ions, like sodium ions in our hybridization medium of double SSC. as you can see here. Therefore, yes.
And the second question about oligonucleotides. Did you buy such oligonucleotides, and where you bought?
Yes, thank you. It is a very crucial question in our work, because such oligonucleotides are, we can say, the most expensive the most expensive equipment, or the most expensive molecule that we use by weight. Their expensiveness was the primary reason. We firstly were compelled to assess the stability, the usefulness of our nanoparticles with the use of lipoic acid, because lipoic acid as a surface blocking molecule is much cheaper, much more cost effective than oligonucleotides. After we saw convincing results with our previously developed gold nanoparticles, we safely moved on to use higher concentrations of oligonucleotides. These oligonucleotides are bought from Metabion. They are synthesized in Germany. Did I answer your question?
Yeah.
Thank you.
Thank you so much. Thank you for your work.
Also, I have a question. You showed us the graph of distribution of your nanoparticle sizes. I want to ask, which method did you use? You make some nano images, so you probably measure the visible spectrum and analyze plasmon resonance. So how you measure this diameter?
Yes, thank you. It is my mistake that I didn't specify the method. It was correlation spectroscopy. The instrument we used to obtain such distributions is called Malvern Zeta Sizer, and the name of the method we used. Let me check my
Okay, you can later write the answer in the chat of Zoom, and I will check it later. Okay. And also, I want to ask
photon correlation spectroscopy.
Okay. And can you move to the next slide also? Next. The next slide. Can you explain what is on the axis of this graph? Also, you can barely see it.
This is thank you. This is a sensorgram of SPR-based DNA hybridization biosensor on the x-axis. There is time measured in minutes. On the y-axis, there is sensor response of the biosensor, which is measured in angle degrees. The working principle of SPR spectrometry is dependent on the exact angle at which we detect the phenomenon of surface plasmon resonance. This exact angle is dependent on the mass of molecules that are adsorbed on the surface, on the sensor surface of the biosensor.
Thank you, because this method was not clear for me. It's quite new. And we have also one question from the poll.
Thank you very much for your presentation. As I understand, your nanoparticles were the spherical form.
Yes. We were using gold nanospheres.
On your opinion, can the change of form of nanoparticles enhance their properties for your work?
This is an interesting question, and it is connected with the phenomenon of localized surface plasmon resonance, which takes place on nanoparticles of different shapes. Here, we are dealing with the phenomenon of surface plasmon resonance, which is useful because when we backtrack on the working principle of our biosensor system, it is used to probe the composition of a surface layer with the thickness of about 200 nanometers. This height, allow me to draw, this very height of our sandwich structure can be up to 200 nanometers tall. When we are dealing with a localized surface plasmon resonance, which takes place on the surface of nanostructures like different nanospheres, nanorods, nanostars maybe, we are dealing with heights of up to 6 nanometers, which is why, in our opinion, only the mass of the nanoparticle matters, not its form.
Okay, thank you very much for the answering. Thank you for the questions and for the presentation. We will move forward I see that we have more questions in our Zoom, but we have limited in time, so please let's continue the discussion in the chat. And we will move forward to our next speaker, PhD student Maria Hutko from the Lashkarevo Institute of Semiconductor Physics of NASA of Ukraine.
Good afternoon, dear colleagues. My name is Maria Hutko. My work is about photochemical synthesis of silver nanoparticles recorded with polyionization and simulation. Nanoparticles is used in different areas, for example, sensors, diagnostics in body, and drug delivery. To use these nanoparticles, it is very useful to manipulate its properties. For example, the coating of this nanoparticle. And one of the most useful methods is polymer coating. In our work, we try to use first of all the substitution of typical tetrad coating nanoparticles by this polymer. However, we met the problem that these nanoparticles aggregated, and then decided to use the simultaneous synthesis of polymer with the formation of the nanoparticles. To achieve this purpose, we used a special reagent, which I will call inverter in a further discussion. It is specific because it has this part like initiator of polymerization and also a dual group for better attaching to the nanoparticle. It is very useful to find a better sequence of the addition of reagents and manipulate some parts of these reagents. So we found the most ideal sequence is using monomer for polymerization, silver nitrate for forming silver nanoparticles, sodium biohydrate, and this inverter. And also we used ultraviolet irradiation to make the time of the red to make these reactions more faster. It's typically used in different studies by the scientists. Also, it's very important to investigate different times of this irradiation to achieve the most ideal level of particles, which will be stable by time and don't aggregate. For simulation, we used mist-scattering theory that is based on the different optical constants of the materials and environment. In our case, it will be silver and water. You may see the black curves. It's a real spectra of our nanoparticles in different stages of the synthesis. And we may observe that in most cases, it has two main peaks, which correlate to different sizes of these nanoparticles. In our model, we try to approximate these curves to the real spectrum. However, it appeared to be quite difficult because there is too many effects in these solutions. Also, there is some limitations of the model. For example, in this case, the second peak is about 650 nanometers, and in our model, we don't even observe this peak. And in further investigation, we will try to solve this problem. Also, it's really quite difficult to make a full approximate spectrum. That's why then I use two different spectrum of simulated curves, which is more approximate to the real peaks of our nanoparticle. Also, it's very necessary to say that the dominating part is about 400 nanometers, which is quite close to the straight nanoparticles, which is typically synthesizes from 4 to 8 nanometers. That's why we use these models to investigate the real sizes of our nanoparticles, also using different methods, for example, atomic force microscopy and dynamic light scattering. However, these two methods also have some limitations. As you may see from the quality of this photograph, we can't clearly see really tiny nanoparticles that are less than 10 nanometers. That's why our model is very necessary to calculate these sizes. In first case, you may see that it had the 2 or 3 dominating fractions of the sizes, and depending on the methods of calculations, these sizes may have a bit different. Also, it's very necessary to say that in our model we didn't calculate shell of the nanoparticle. It's a polymer particle. It's not quite high, so in this stage of the investigation, it's not so necessary. Also, we don't know for sure if it's really the bigger nanoparticle or just the aggregates, because mist-scattering theory also has some limitations to calculate the aggregation part, because it's a very very difficult process to find out. In other photographs, we still may observe some parts about 10 nanometers. However, it's still quite difficult to see them with high quality. When we change the time of the irradiation of our nanoparticle during the synthesis, we may observe that when we when we irradiate for 15 seconds longer, the general average nanoparticle sizes may be quite lower, and it doesn't depend on the fraction, because in all fractions they are bigger than previous. For example, from IFM studies, in the middle fraction, the sizes of nanoparticles changes from 22 nanometers to 14. From synthesizer as dynamic light scattering method, it changes from 97, and from the model, from the 33 to 24 nanometers. And also you may observe that depending on the spectral properties and calculated model from it, so we may observe that the dominating fraction is still really tiny nanoparticles, about 2 nanometers. If we change the irradiation time of the second step after the addition, initiated polymerization, these nanoparticles become quite big and may also aggregate. This we may observe in this two model spectra. The lower, for example, lower fractions from lower fraction from 22 nanometers to 53, which is quite big. However, it's very useful to use this model, as I said before, because we can see these really tiny nanoparticles, for example, from AFM. There is no such fraction. In dynamic light scattering, it's not so high. However, we know that the dominating fraction in our assets. So to conclude, we used a new method of this 7 nanoparticle synthesis that we proposed through the simultaneous formation of the presence in sodium hydrate and isopropyl which is undergoing polymerization by UV radiation to prevent stabilizing the PENIPAM layer on the 7 nanoparticle synthesis. We also propose spectral and morphological properties in studies in the range of absorption from 380 nanometers to 430 nanometers, so which corresponds to the lowest size fraction of these nanoparticles, above 10 nanometers. And also, we observed the size parameters of these 7 nanoparticles and analyzed them depending on the different time of UV radiation and compared them to the experimental data. So to conclude, when we choose the ideal parameters of the synthesis, the average nanoparticle size declines with decreasing the first irradiation time up to 15 seconds. And after the addition of initiator polymerization, they grow from with using the second irradiation down to the 30 seconds. The particle size also may increase. Thank you.
Okay, thank you very much for the presentation. Do you have any question at all? Yes, we have.
Please tell us what irradiation wavelength you use to initiate polymerization and nanoparticle formation. So I saw UV1, UV2. So what
There is no, it's not a laser, it's just a lamp. So the wavelengths may be different from time to time. In the range between 300 meters to 400, as I remember right.
Thank you very much. Do you have any more questions? If you have a question in Zoom, please ask. Seems like no more questions, so thank you very much. And our next speaker, student Viktor Kuznetsov from Lashkarev Institute of Semiconductor Physics of NASA of Ukraine. Viktor, are you with us?
Yes, I'm here.
So please share your screen and start.
Okay. Can you see the screen now?
Yes, we can. Please start.
Okay. My work, I'm Viktor Kuznetsov, and our work is about comparison of fluorescent quenching efficiency for different organic fluorophores as neutroaromatic explosive sensors. In this study, we focused on fluorescence quenching technique for detection of explosive molecules. Most of commonly used explosives contain either NO2 or NO2 or NH-NO2 molecules, which are electron deficiency groups. Purine sensing abilities are based on photoinduced electron transfer, or PET, and this is a process where an electron transfers between a donor and an acceptor molecules, and it happens upon photoexcitation. Therefore, in the presence of some neutral groups, purine shows fluorescence intensity quenching due to transfer of the electrons that are responsible for fluorescence properties. So this effect can be further amplified using some plasmon-enhanced fluorescence phenomenon induced by metallic nanoparticles. And in this way, we can develop a sensor for trace detection of different explosives. Here, fluorescence quenching effect of purine was compared to other organic fluorophores with similar fluorophores band. Around 360 nanometers excitation, which is visible emission. Namely, these fluorophores are F8BT, polyphenylvanillin, and derivatives MAH-PPV and PPMH-PPV. So we can start with purine fluorescence characteristics. Purine was chosen as a reference point in our work because it's well known for its fluorescence properties and its fluorescence quenching as well in the presence of the neutroaromatic explosives and their analogs. All solutions were prepared in THF solvent to ensure solubility for all fluorophores with a concentration of 1 milligram per milliliter. Then 500 milliliters of this solution was deposited as a thin film onto a glass substrate via spin coating technique. Purine fluorescence abilities are demonstrated on photos at the top. Left one is null excitation with room lights on, middle one is excitation with room lights on, and on the right you can see excitation with room lights off. So excitation can be seen more clearly. 3D fluorescence spectrum on the left shows that Puran exhibits excitation peaks at 360 nanometers and two emission peaks at 385 nanometers for monomer and 460 to 470 nanometers for excimer. Quenching was studied for the longer wavelength peak in the visible spectrum. We studied Puran fluorescence quenching by 4NP. In the presence of 4-nitrophenol, Puran fluorescence starts quenching significantly even with very low 4NP concentrations, such as 10 in the power of -9 moles, showing 49% quenching. At concentration of 10 in power of -2 moles, it shows 97.5% quenching. Also, we studied quenching by 4NT or 4-nitro-2N. In presence of this substance, Puran shows similar behavior. Comparing with 4NP, its fluorescence starts quenching significantly even with small concentrations, such as 10 in power of -12 moles, showing nearly 40% quenching. However, in percentage comparison with addition of maximum concentration, which is 10 in power of -2 moles, its quenching is a bit lower than for 4NP, 86.7%. Then we studied fluorescence characteristics of MAH-PPV. It was chosen as fluorescent polymer exhibiting fluorescence quenching in the presence of neuroaromatic explosive molecules and their analogs. MAH-PPV fluorescence abilities can be seen on photos at the top. Also left is with no excitation with room lights. On the middle you can see excitation with room lights on, and on the right excitation without room lights. 3D fluorescence spectrum on the left shows that MAH-PPV exhibits strong excitation in the range of 300 to 380 nanometers and emission peak in the range in 570 to 620 nanometers. MAH-PPV fluorescence quenching by 4NP. In the presence of 4NP, for this fluorophore, quenching starts not so fast as for Puran in the low concentration region, such as 10 in power of -6 moles, showing 28% quenching. However, at a concentration of 10 in power of -2 moles, it shows 99.3% quenching, which is slightly higher than for Puran. Also, we studied quenching for this fluorophore by 4NT. In the presence of 4NT, it shows quenching not so fast as for Puran in the low concentration region, such as 10 in power of -6 moles, showing 21% quenching. However, at a concentration of 10 in power of -2 mole, it shows 45.5% quenching only. Also, we studied PMAH-PPV fluorophore and its characteristics. It was chosen as another fluorescent polymer exhibiting fluorescence quenching in the presence of neuroaromatic explosives and their analogs. Its abilities can be seen on photos at the top left with no excitation with room lights, on the middle excitation with room lights, and on the right excitation without room lights. A 3D fluorescence spectrum on the left shows that PMAH-PPV exhibits excitation peak in the range of 320 to 380 nanometers and peak emission in the range of 520 to 570 nanometers. Quenching by 4NP. In the presence of 4NP, this fluorophore shows very slow quenching, and at a concentration of 10 in power of -2 mole, it shows only 33% quenching at 525 nanometer peak and 32.7% at 545 nanometer peak. Quenching by 4NT. In the presence of this analyte, fluorophore shows better quenching than 4NP, showing 27% quenching at a concentration of 10 in power of -6 mole. Moreover, at a concentration of 10 in power of -2 mole, it shows 47.5% quenching. And the last fluorophore we studied in this work is F8BT fluorophore. It was also chosen for the same properties, and you can see it in three images on the top. The left one is without excitation with room lights, the middle one is excitation with room lights, and the right one is excitation without room lights. 3D fluorescence spectrum on the left shows that this fluorophore exhibits excitation peak at around 360 nanometer and emission peak in the range of 530 to 580 nanometers. Quenching by 4NP, it starts quenching even in the very low concentration region. Total quenching at a concentration of bigger concentration of 10 in power of -2 mole is 41%. And quenching by 4NT in presence of 4NT, Fa8BT shows similar behavior when comparing with 4NP. Its fluorescence starts quenching even in the low concentration region, such as 10 in power of -12 mole, showing 7.5% quenching. However, in percentage comparison with addition of maximum concentration at 10 in power of -2 mole, its quenching is a bit higher than for 4NP, 43%. Here you can see comparison of quenching for different fluorophores. As you can see, the best quenching is exhibited by Pyrene for both 4NT and 4NP analytes. MAH-PPV shows very high quenching for 4NP, but mediocre one for 4NT. Other fluorophores achieve quenching near 30 to 45% for both 4NP and 4NT. Conclusions are that it was found that almost complete N-partial quenching. Pyrene has 98% and MAH-PPV 99%, and about partial ones, PMH-PPV has 48% and F8BT has 33%. It's possible for high analyte concentration, around 10 in power of -2 mole at different emission wavelengths. At low analyte concentration, fluorescence quenching up to several tenths of percent was registered, with most expressed quenching observed for Pyrene, which has 49% for 10 in power of -9 mole solution of 4-nitrophenol. Pyrene and MAH-PPV fluorophores are promising as a basis for the development of a plasmon-enhanced fluorescence sensor for trace detection of explosives. Acknowledgements. This work was supported by the National Research Foundation of Ukraine. Here you can see the number of projects and its name Portable Sensor Platform based on plasmon-enhanced fluorescence for explosive detection. Thank you for your attention.
Thank you very much for the presentation. Do we have a question on the phone? Yes, we have one question.
Thank you for your presentation. We see that your detecting method is based on the fluorescence quenching. Fluorescence quenching the fluorescence from donor fluorophore by acceptor exposure. So, is it right that to be detected by your method?
Sorry, can you repeat the last part?
To steal? Sorry?
Can you please repeat?
Repeat, please.
Yeah.
Sorry, should an explosive be an electron acceptor to steal an electron from fluorophore to capture this electron? Yeah. So your explosives to be detected by your method should be electron accepted. Is it right?
Yes, it's right.
Sounds good. Most of contemporary or currently used explosives are nitro compounds, and that is why your method is is more or less universal. Yeah, is it so?
Yes, most of commonly used explosives are working the same way, so they can be detected by our sensor. Yeah.
Yeah, thank you.
We have one more question. Moment.
It's a nice presentation. The question is, do you have any idea how to distinguish between different explosives when it comes to consumer sensitivity? It's going to be how to develop selective sensors.
Sorry, I was hearing you a bit bad, but as I got your question,
Question is how to provide selectivity.
Okay.
How to distinguish between different explosives.
There is a problem with this part of our sensor, but we have several ideas for solution. In the current state, it's not selective for different kinds of explosive because all of them are still in electrons and are working as the same way. So the most prominent idea to get selectivity is to add a layer of a MIP or molecular imprinted polymer, which will be selective for exactly the same explosive which we need. So we can have an array of sensors with different MIP layers, and each sensor with a unique MIP layer will be selective for only one and only explosive. Yeah.
So you want to create some kind of a filter before your before your device.
It will
Okay.
like prevent other type of explosives to be detected by the sensor. It will like be like a filter layer on the top of it.
Okay. Any more questions? No more questions. So thanks once again.
Thank you.
And this was the last speech for our section nanoplasmonic and surface enhanced spectroscopy. It was an honor to me to be a chairman of this section. And we will move forward to our next section, nanobiotechnology for healthcare, where the chairman will be Oksana Butnik.
Thank you very much, Andrei, for this introduction of myself. Good afternoon, my dear colleagues. Welcome to the session, say, biotechnology, nanotechnology, and healthcare. And the first our speaker will be Dr. Anton Tkachenko from the Institute for Problems of Heart and Biology and Biomedicine of the Nancy Hospital. Please take the floor.
Good afternoon. Can you hear me?
Yes, yeah.
I'm going to share my presentation. So is it visible? Can you see it?
Yes. Now, yes.
Yeah, great. First of all, I would like to express my gratitude for the opportunity to present my research here. And in this talk, I'm going to introduce eryptosis assays as an efficient and actually quite novel tool to analyze the toxicity of nanomaterials. In general, the toxicity of nanomaterials is one of the major limitations that actually restrict their application, practical application in clinical practice. And the overall evaluation of toxicity is quite challenging and multi-step process. And upon systemic administration, nanomaterials actually contact with blood cells and blood components. That is why the evaluation of blood compatibility of nanoscale materials is a crucial step and actually essential step in the overall assessment of nanomaterials safety. So in general, red blood cells or erythrocytes, which are actually the most abundant cells in circulation, they are very convenient models for toxicological research, including the nanotoxicological research. This is associated primarily with their structure. They have quite simplified structure compared to other cells, nucleated cells, though they lack organelles, and they are considered as just sex-carrying hemoglobin protein that is involved in transport of oxygen. Moreover, erythrocytes have a limited set of metabolic pathway and signaling pathway, and that is why erythrocytes have less diverse cell death machinery. In our recent papers, we have summarized recent advances on the cell death research in erythrocytes. Yes, so fundamentally, erythrocytes can undergo two types of cell deaths associated with eryptotic, so-called eryptotic morphology, and hemolytic morphology. So eryptosis is a regulated cell death of erythrocytes, which is more physiological and similar to apoptosis of nucleated cells. At the same time, they can undergo hemolysis, which is an accidental cell death mode, which occurs in response to mechanical damage of erythrocytes. At the same time, they can also undergo necroptosis, which is a regulated form of hemolytic cell death. So in this study, I'm going to focus on eryptosis induced by manganese oxide nanomaterials. And briefly, let's take a look at the signaling machinery of eryptosis. So because erythrocytes, they have quite simple structure, and actually they express only two caspases, which are critical for cell death of nucleated cells. They have a little bit different machinery compared to apoptosis. In particular, the key role, the master regulator of eryptosis, is calcium ions. So there are different signaling pathways that activate calcium influx inside erythrocytes, like ceramide, like reactive oxygen species, like some eryptosis regulating kinases. But in eryptosis, the key event is the elevation of intracellular calcium ion. However, there are also calcium-independent mechanisms that are involved in eryptosis, but it is important to note that all these mechanisms finally culminate in activation of the enzyme scramblase, whose function is to translocate phosphatidylserine molecules on the surface of erythrocyte. So this is like a hallmark of eryptosis, phosphatidylserine externalization, because it is used as a eat-me signal for macrophages, and using these phosphatidylserine molecules, macrophages phagocyte erythrocytes, removing them from the circulation. What are the physiological functions of this process? So first of all, elimination of damaged erythrocytes. The lifespan of erythrocytes is approximately 120 days, and when they are damaged, exposed to different stresses, like oxidative stress, for example, or something else, they should be eliminated in order to ensure the turnover of red blood cells and the maintenance of the population of functional cells. So within minutes following exposure of phosphatidylserine on the surface, erythrocytes are removed by macrophages. And also it prevents hemolysis, which is a lytic cell death of erythrocytes. When during this lytic cell death, they release toxic molecules like damage-associated molecular patterns, which are toxic for kidneys, for example, and also can promote inflammation. In addition, eryptosis is involved in the host immunity as an anti-malarial mechanism. How is it related to nanotoxicological research? Currently, hemocompatibility of nanoparticles is evaluated. However, there are no standard guidelines. Mostly, the toxicity is evaluated using hemolysis assays, which are non-specific because hemolysis just reflects the mechanical damage and doesn't provide any insight into the mechanisms through which erythrocytes elicit their toxicity. So take-home message is that hemolysis is currently the most common approach to detect the hemocompatibility of nanomaterials. However, in one of our papers, we have summarized what are the pros and the cons of hemolysis and eryptosis assay. And our analysis reveals that eryptosis is much more effective than hemolysis in relation to toxicology, and in particular nanotoxicology. Here you can see on the slide the summary of all the benefits of eryptosis assay. However, I want to underscore just two of them. First of all, higher sensitivity of eryptosis assays compared to hemolysis assay. And in addition, the opportunity to provide insights into the molecular mechanisms of nanoparticle-induced toxicity, because hemolysis is not associated with any signaling pathways. It's just a mechanic destruction of cells, while eryptosis is associated with a specific eryptotic machinery we have already discussed today. So these are the key advantages of eryptosis assays. Here again also we have summarized the nanotoxicological studies, yes, where eryptosis was used as a tool. There are approximately more than 12 of such studies, different nanoparticles of different structures, mostly metal-based nanoparticles or metal oxide nanoparticles were used. And as you can see, calcium signaling and generation of reactive oxygen species, the oxidative stress, were the key contributors to the toxicity, erythrotoxicity of these nanomaterials. So in this study, we investigated how manganese oxide nanoparticles affect the eryptosis, and also investigated the mechanism of this manganese oxide nanoparticle-induced eryptosis. You can see the characterization of the synthesized nanoparticles. They were kindly provided and characterized by our colleagues from the Institute for Scintillation Materials of the National Academy of Sciences of Ukraine. So you can see that the average size of these nanoparticles was approximately 16 nanometers. So they were 16 nanometers in diameter. So several flow cytometry-based and confocal microscopy-based approaches were used to detect eryptosis. Initially, we assessed, in general, the erythrotoxicity using routine hemolysis and osmotic fragility assays. And as you can see, the nanoparticles didn't increase the osmotic fragility of erythrocytes, and induced eryptosis only at the highest, induced hemolysis only at the highest concentration, 80 milligrams per liter. At the same time, eryptosis assay and phosphatidylserine externalization, as I said, is a hallmark of eryptosis, so it's a generally accepted approach to detect eryptosis. So using this phosphatidylserine externalization detection, we figure out that at concentration starting from 40, these nanomaterials could induce eryptosis, and the effect was dose dependent. So as I mentioned, eryptosis is more sensitive. It shows the toxicity at lower concentrations compared to hemolysis and especially osmotic fragility assays, which are still quite common. The mechanisms that we discussed, so we evaluated the key signaling molecules involved in eryptosis, in particular calcium signaling. So it was calcium levels were elevated in cells, in erythrocytes exposed to the manganese oxide nanomaterials. In addition, the levels of reactive oxygen species and reactive nitrogen species were elevated, indicating that erythrocytes underwent oxidative and nitrosative stress in response to these manganese oxide nanoparticles, which is also common for metal nanomaterials since they are redox active. Reactive oxygen species cause damage to membrane, causing lipid peroxidation and general damage to the membranes. And we used an R12S probe, which is membrane sensitive, it's lipid order sensitive, to detect the lipid order of the erythrocytes exposed to these nanomaterials, and elevation of the fluorescence of this probe indicated the decrease in the lipid order of erythrocytes. Also, these nanomaterials upregulated the activity of enzymes caspases, caspase 3 and caspase 8. These caspases are actually crucial for apoptosis of nucleated cells. However, their contribution to eryptosis is limited, so they are not essential for the execution of eryptosis. However, still, our study revealed that manganese oxide nanoparticle-induced eryptosis was caspase dependent. So here you can see an example of confocal microscopy-based study, which clearly shows that using the calcium-sensitive probe, it was clearly demonstrated that calcium elevation was associated with eryptosis of erythrocytes exposed to manganese oxide nanoparticles. So to sum up, manganese oxide nanoparticles show good hemocompatibility at low concentration. However, at high concentration, they induce eryptosis, in which oxidative stress and caspase-dependent mechanisms play a key role. And eryptosis dissection is more sensitive, so our data are in line with other studies, confirming a higher sensitivity of eryptosis assays compared to hemolysis assays. And eryptosis can be included as a supplement for nanotoxicological studies, especially for hemocompatibility studies. So I would like also to express my gratitude to the colleagues like from Ukrainian institutions and those that are located abroad for their contribution to this study. And I would like to say that we are open for collaboration with manufacturers of nanoparticles if they want to assess the toxicity of their nanomaterials. Thank you for your attention.
Thank you very much, Leon, for a very interesting presentation, very interesting results of that presentation. And I would like to ask about a question. Yes, we have a question, that's right.
Thank you for your presentation, and I'm sorry, maybe I have missed something in your presentation, and I'm sorry for my ignorance, but why is it so important to know that manganese oxide can trigger hemolysis or erythrosis? So is it a compound which is frequently found in biological media, I mean manganese oxide? So why is it interesting for us that this oxide triggers hemolysis and erythrosis?
Yeah, thank you for your question. Actually, manganese oxide nanoparticles are widely studied as potential pharmaceutical agents, especially as potential anti-cancer drugs. So both in its pure form and as a modified ones, yes, in combination, or as drug delivery system. So their primary application is application as anti-cancer agents and drug delivery systems for anti-cancer agents. That is why in this case, they will be administered systemically, yes? And in order to be delivered to the target, to cancer cells, they should pass through blood, actually, through circulation. They will be delivered there in the bloodstream. So that's why they will contact with components of blood vessels, blood cells, vascular endothelium, and so on and so on. So that's why it's important to assess how do they interact with blood components.
Thank you for explanation, and maybe someone have more questions. Yes, please.
Thank you for interesting presentation. One question. And what about the translation of your in vitro study in some of the beams? You can check with them.
Yeah, thank you. Sure. Yeah, this is like the most important thing, yes, to investigate them further. We actually focus primarily at the moment on the screening of nanomaterials in general to develop large-scale screening models for that. We haven't assessed this particular manganese oxide nanomaterials in vivo. However, we have experience with in vivo studies of other nanomaterials, in particular like gadolinium yttrium vanadate nanoparticles doped with europium ions. So we studied how do they affect erythrocytes in vivo. Yes, so and very promising result was shown for these nanoparticles. However, as the next step, of course, in vivo studies are obviously should be like performed. Obviously should be performed.
Thank you very much for explanation. And maybe see more question. We limited also in time. So on top, thank you very much again for the presentation. And we have to, yeah. We have the next forward, and the second our speaker will be Dr. Vladislav Semenko from the Institute of Scintillation Materials in Ukraine. Please, Vladislav.
Can you see my presentation?
The floor is yours. Yeah, we can.
Okay, okay, everything okay, yeah. Okay,
yeah, you
so
can start.
yeah, okay. So at first I'd like to thank the organizers for the possibility to take part in this conference. And my report is called Reversible Luminescent ROS Sensors based on colloidal solutions of cerium oxide nanoparticles. And first about ROS or reactive oxygen species. Why are they important and why do we need to sense them in living cells? Reactive oxygen species include superoxide anions, hydrogen peroxide, and hydroxyl radicals. And they are ubiquitous in living cells. They are formed during oxygen breathing. They are formed under influence of ionizing radiation. And they can be both useful and dangerous. When the concentrations of reactive species is low, they can be used for signal transduction or for immunity response. But if the concentration of ROS is too high, it can be dangerous to living cells, leading to destruction of some cells organelles and so on. So we need to detect in some way the concentration of reactive oxygen species. And hydrogen peroxide is the most stable form of reactive oxygen species, and it's more easy to detect its concentration than of other ones. In recently, the number of luminescent sensors of hydrogen peroxide content in living cells were proposed. These sensors are based as on organic molecules, so on inorganic nanoparticles. And both these classes of sensors has their own advantages and drawbacks. The advantages of organic molecules are high sensitivity, high selectivity, low detection limit, and biocompatibility. But at the same time, they have some sufficient limitations. They are useful, non-reversible, they have low stability, and also they have photobleaching. At the same time, inorganic nanoparticles, including rare earth-doped nanoparticles, they are highly stable, they have no photobleaching, and as I will show you, some of these nanoparticles are reversible, have reversible luminescent signal. At the same time, they suffer from moderate sensitivity and also low or moderate selectivity. At first, the rare earth-doped nanoparticles for sensing of hydrogen peroxide were proposed about 15 years ago in this paper, where the European luminescence of yttrium vanadate nanoparticles were used to measure the content of hydrogen peroxide in both water solutions and living cells. The mechanism of sensing was based on the dependence of europium 3 plus luminescence on the presence of hydrogen peroxide, and they achieved reversibility of their sensors using the combination of addition of hydrogen peroxide and UV irradiation, which turns the signal to initial point, and so these sensors can be used many times. In our own studies, we have shown that cerium oxide nanoparticles, which are very well-known class of nanoparticles as antioxidants, can be also used as efficient hydrogen peroxide sensors due to cerium 3 plus luminescence, which is inherent for these nanoparticles. Namely, when we add hydrogen peroxide to colloidal solutions of these nanoparticles, the intensity of this cerium 3 plus luminescence decreases due to oxidation of cerium 3 plus to cerium 4 plus, and the decrease of this luminescence is proportional to the concentration of hydrogen peroxide in water solutions. Moreover, due to some intrinsic properties of cerium oxide, the luminescence sensors based on these nanoparticles are reversible. So after addition of hydrogen peroxide, after some time, the initial luminescence signal becomes as it was before the hydrogen peroxide addition. This reversibility makes this class of sensors very interesting due to this difference from the most of sensors which are known for today. This reversibility also can be increased in time from tens of hours without UV radiation or something like this to about 40 minutes when we apply UV radiation after hydrogen peroxide addition. Moreover, the luminescent signal for these nanoparticles, as you can see, it depends on the concentration of hydrogen peroxide, and this dependence is linear in semi-logarithmic coordinates, which also is useful when we apply these sensors. So it's about nanoceria without any doped ions, and it was interesting for us to try also doped cerium oxide nanoparticles as possible ROS sensors. We have chosen the europium ions. Europium ions are widely used in the different types of luminescent sensors due to some advantages, such as deeper penetration of red light into the tissues, also a high noise ratio due to autofluorescence of most cells in the blue-green range, while europium 3 plus demonstrates luminescence in red range. And also the possibility of use the ratio of europium 3 plus bands instead of the luminescence intensity itself. And I will show you how it can be useful for our sensors. So we have obtained two types of nanoparticles with different sizes, about 3 nanometers and 6 nanometers. These nanoparticles all were of fluoride structure, which was confirmed by XRD results. And then we studied the luminescence spectra of our nanoparticles with addition of different concentration of hydrogen peroxide. And we observed that as cerium 3 plus luminescence band, so europium 3 plus luminescence band, they were both dependent on the concentration of hydrogen peroxide in the wide range. And these dependencies were seen both for 3 nanometer and for 6 nanometer nanoparticles. However, the range for this depends for different sizes of nanoparticles were also different. We tried to understand what is the nature of this hydrogen peroxide induced luminescence question, and mainly in the scientific publications, the quenching of luminescent nanoparticles by hydrogen peroxide is explained by the dynamic quenching by Stern-Former model, and we also try to apply Stern-Former or modified Stern-Former model to our results, and we see that this model is not applicable. The curves are nonlinear. So in our case, the dynamical quenching can be ruled out. And instead, we have applied some well-known absorption models, such as Langmuir, Florendijk, and Tomkin models, because we consider that hydrogen peroxide would first adsorb on the surface of our nanoparticles, and after this we have since quenching. And really the adsorption models of Langmuir and Tomkin, but not Freundlich, works very well in our case. So indeed we can say that quenching of both cerium 3 plus and europium 3 plus bands in our nanoparticles is mediated by hydrogen peroxide adsorption on some surface sites of these nanoparticles. What are these surface sites? I will show you somewhat later. At the same time, we have the different behavior of decay curves for these bands. While addition of hydrogen peroxide doesn't change the decay of cerium 3 plus luminescent band, for europium 3 plus increase of hydrogen peroxide concentration leads to a decrease of decay time. So it can be concluded that while for cerium 3 plus we have the decrease of the content of luminescent centers, cerium 3 plus ions which turn into cerium 4 plus due to oxidation by hydrogen peroxide. For europium 3 plus ions we have some different mechanism. Namely, we have some kind of energy transfer which decreases the lifetime of some optical centers. And we have suggested that as quenchers can be the hydroxyl groups formed at hydrogen peroxide decomposition. To confirm this supposition, we have determined the concentration of hydroxyl radicals formed at hydrogen peroxide decomposition for nanoparticles with different sizes, and we really observed that for both types of nanoparticles, the content of hydroxyl radicals increased at hydrogen peroxide addition, and this increase was sufficiently more for 6 nanometer nanoparticles, which agrees very well with the decrease of the intensity of europium 3 plus luminescence center, namely for 6 nanometer nanoparticles as well. So we have concluded that these processes should be in some way connected, and really hydroxyl groups can be quenchers in our case for europium 3 plus luminescence. These results allowed us to confirm the model of hydrogen peroxide sensing for small and large. Small means 3 nanometer and large means 6 nanometers in our case nanoparticles, while for small nanoparticles the dominant type of surface centers are cerium-3 plus oxygen vaccine cerium-3 plus complexes. These complexes were confirmed before for pure nanotheria. And for large nanoparticles, the main type of centers, surface centers, is cerium 3 plus oxygen vacancy, europium 3 plus center. And interaction of hydrogen peroxide with this center leads to formation of hydroxyl radicals, what we can see on the results of the content of hydroxyl radicals for different sizes of nanoparticles. So it's about turn-off sensing, and a couple of words about radiometric sensing. We can see that not only the general intensity of europium-3 plus luminescence decreases after hydrogen peroxide addition, but also the ratio between different europium-3 plus bands changes after addition of hydrogen peroxide. It's well known that europium-3 plus ions have two different transitions, 5D0-7F1 and 5D0-7F2. First is magnetodipole transition, which is insensitive to the local surrounding of europium ion, and second one is electrodipole, which is extremely sensitive to the surrounding of this ion. So presence or absence of oxygen vacancies, for instance, near europium ion can change the ratio of these bands. And we can see that increase of the concentration of hydrogen peroxide also increases the ratio between magnetodipole and electrodipole transition. So when we add hydrogen peroxide, the local surrounding of europium ions in some way became more symmetrical. Why can it be? It can be when the initial surrounding of europium ion has oxygen vacancy, and after addition of hydrogen peroxide, we see the decrease of the quantity of oxygen vacancies due to change of oxygen stoichiometry of nanocrystal, and we have more europium ions with ideal surrounding, which non-defect surrounding, which favors this 5D0-7F1 luminescence. So summarizing our results, we have obtained cerium oxide europium doped nanocrystals with three possible channels of hydrogen peroxide sensing. First one is cerium 3 plus luminescence intensity, which is determined by hydrogen peroxide absorption on the surface of cerium oxide nanoparticles, which followed by cerium 3 plus, cerium 4 plus oxidation. Second one is europium luminescence, which is quenched by possibly hydroxyl groups formed during hydrogen peroxide decomposition. And the third channel is the ratio between europium bands due to change of the local surrounding of europium ions at hydrogen peroxide absorption. So up to conclusions, the hydrogen peroxide sensors of different sizes were obtained by the method of colloidal synthesis. This sensing is provided by concentration dependence of intensities of europium and cerium 3 plus luminescent band, as well as hydrogen peroxide sensitivity of the ratio of europium transitions. Hydrogen peroxide is based on sensing is based on the cerium 3 plus, cerium 4 plus oxidation, quenching of europium luminescence by hydroxyl groups, and change of local surrounding of europium ions. And the ability of these nanoparticles to both turn off and radiometric sensing increases the reliability of nanotheria-based sensors, enable multi-channel hydrogen peroxide detection in different spectral ranges. I want also to thank the National Research Foundation of Ukraine for their continuous support of our work. And thank you for attention. I'm ready for your questions.
Thank you very much, Vladislav, for your valuable contribution. And I would like to ask, do we have any question from conference call? Yeah.
Thank you very much for the interesting topic. And my question corresponds to processes on the surface of nanomaterial. It is close to classical Fenton reaction on the surface of the magnetites, the surface of Fenton reaction.
As I had understood, you asked about Fenton reaction, yeah?
Yes, Fenton reaction on this
Yes.
surface nanomaterial.
Yes, we have seen that while for pure nanomaterial without doped ions, so for small European doped nanoparticles, we have no Fenton reaction, so the content of hydroxyl radicals is rather low when we see the decomposition. Its main mechanism, as we think of this decomposition, is something like this. So the specific surface structure of nanomaterial allows to prevent the formation of hydroxyl radicals during hydrogen peroxide decomposition. But it is not the case when we dope these nanoparticles, especially for large nanoparticles, when the dominant types of surface centers are cerium-3 plus oxygen vacancy, europium-3 plus centers. So in this case, we really have something like Fenton reaction, and indeed we have the high content of hydroxyl radicals, which we can see also from this result. You can see on this slide.
Thank you. Maybe one more question. Okay, since everything now is clear, thank you again, Vladislav, for your presentation. Yeah. And the next talk will be given by Dr. Vladimir Prokopiev from the Institute of Surveillance of Biology and Nanotechnologies as awareness of the aim. Please begin your presentation.
Okay, can you hear me? Can I share my screen?
We're waiting for your screen and we can hear you.
Okay, can you see my presentation?
Okay, now, yes, now we can see everything right.
Thank you. First of all, I want. First of all, I want to thank the organizer for the possibility to present the result of our work. Our work, it's a collaboration between some institution. Our colleague, chemist from Institute of Scintillation Material have synthesized some nanoparticles, and we in our institution conduct research on the biological property of these nanoparticles, and I'll talk think about our research in general. Okay, next slide. Manganese is essential but not widely available trace element. It plays a role in antioxidant defense, cell death mechanism, ATF metabolism, some immune reaction, bone regeneration, in reproductive health, and some nanobiomaterial with manganese can be used like drug delivery system, like anti-cancer agent, and in activation and inactivation of some enzyme. But before using this material, we have to find the balance between efficiency and toxicity of this material. And in our work and in all nano biomaterial research, we have 4 different stages of research. First of all, it's research in cell-free systems. That means nanoparticles or biomaterial characterization and some properties, for example, antioxidant properties. The second big part, it's in vitro study. First of all, it's gamma compatibility because all elements usually contact with blood. First of all, with erythrocytes. Standard methods are spontaneous hemolysis, osmotic fragility, Ross generation, apoptosis to find some mechanism of cell death. After that is screening study for various cell function. It's often used on some adherent cell culture, nucleated cells that can be something like adhesion characteristic, confluence, membrane integrity, some metabolic test, genotoxicity, proliferation. After that, in cell culture, we can also do some specific study, find the mechanism of action, and we can model in cell culture even pathology. The third variant, it's in vivo study on laboratory animals. Usually it's toxicity, finding a dose and pathology modeling. And the fourth, it's clinical trials, but it can be done only in the big clinical institution. We don't do this. First of all, it's a gamma compatibility, what we have done in this research. Some word about red blood cells elimination. There are different variants of cell deaths in erythrocytes, and our nanoparticles can increase or decrease these variants, and they have its action through this mechanism of cell death. First of all, it's regulated cell death programmed by organism, and accidental cell death. Accidental cell death we have when we have extraordinary toxicity. I can speak about 4 big variants of erythrocyte cell death. First of all, it's aging of erythrocyte, when erythrocyte usually live 120 days, and after that it's have signal like eat me. And for example, it's inversion of membrane, phosphatidylcholine externalization, the lack of CD47 domains, and Ross generation. In this variant, erythrocyte eliminated in spleen by macrophage. The second variant of programmed cell death is ereptosis. In erythrocyte ereptosis, it's variant of apoptosis, but erythrocyte don't have organelles, and it can be activated only with external mechanism. In this variant, erythrocytes also eliminated by macrophage, and these 2 variants of cell death, they are immunologically silent. That means cells don't produce damage-associated molecular patterns and don't activate immune systems. And the second 2 variants, it's necrosis and necroptosis. Necrosis in erythrocyte is hemolysis with production of dumps, and necroptosis is also the variant of programmed cells death when ereptosis can be done. And the right part of these pictures, you can see difference between ereptosis and erythronecroptosis. The K enzyme here, it's a caspase-8. If caspase-8 activated, we have erythroptosis, and when caspase-8 don't active, we can see erythronecroptosis. In this work, we also work with manganese nanocrystal synthesized by Institute of Scintillation Materials. It was already described in the first presentation of this section. The aim of the work was to access the featured cell death signaling in erythrocyte treated with manganese 3 or 4 nanocrystals. In this slide, you can see experimental design. We use rat blood and we incubate red blood cells in Röntgen solution with different concentration of nanocrystal during 24 hours. After that, we do different assays. First of all, is spontaneous hemolysis and osmotic fragility for understand the toxicity of this nanocrystals. After that, when we find this concentration, we use flow cytometry for understand cross generation with fluorescein diacetate eryptosis using annexin 5. And for understand the mechanisms of cell death, we use also necrostatin. It's inhibitor of necroptosis, and vitamin C. It's inhibitor of cross generation. We also use confocal microscopy for detection calcium overload, ROS generation, lipid order change, calpain, and caspase to find the activation of these mechanisms. You already see this picture in the first presentation. I want to say that we find two concentration. First of all, it's 80 milligram per liter. It's a hemolytic concentration. The 20% of red blood cells have a hemolysis, and the concentration 40 milligram per liter already induce eryptosis. The concentration less than 40 milligram per milliliter don't affect erythrocyte. After that, you can see that in this concentration with manganese nanocrystal were activated the generation of reactive oxygen species and reactive nitrogen species. It's for pictures of confocal microscopy. In this kit, green one, it's reactive oxygen species, and red one, it's luminescence of reactive nitrogen species. Also, we use the probe NR20S for detecting the change of lipid order. When membrane more liquid, normal membrane, this probe has green luminescence, and when membrane lose the lipid order with cholesterol, we have red luminescence. We have this effect on the concentration 40 and 80 milligram per liter. The eryptosis detected with annexin 5, it's also the changing of lipid membrane orders, but only with phosphatidyl serine. The next slide, you can see also calpain activation. Calpain, it's an enzyme that take part in cytoskeleton degradation when cells change their shapes. And the last one, you can see in this slide shows the mechanism of eryptosis and necroptosis and the concentration 40 milligram per liter and 80 milligram milliliter. Both caspase 8 H3 were activated. And in the red parts of this slide, you can see that when we add the necrostatin 1, we have no difference in eryptotic cells. No, cells with translocation of phosphatidyl serine. That means the old cells were died from eryptosis, but not from necroptosis. This was one way of the cell death. And the conclusion, toxic concentration of manganese nanocrystals again red blood cells, it's more than 40 milligram per liter. Red blood cells death mechanism of nanocrystallized through calcium, ROS, RNS, caspase, depend eryptosis, and caspase 8 activation is required to eryptosis and prevent necroptosis in response to magnesium 3 or 4 nanocrystals. Thank you for your attention.
Thank you very much for your insightful presentation. And now, let me move to the rest of the discussion. And we will have some questions.
Excuse me, it's problem to hear you.
Okay. Okay. Thank you very much for your excellent presentation. Can you hear me? Yeah. Yes.
Yeah. Now, yes.
Yeah. Okay. So super. And it seems that you are for all topics and explained everything perfect. That everything is clear. And we cannot question to the presentation, and we just want one again to say you thank you.
Okay, thank you.
So yeah. And we're going to and I would like to introduce you our next speaker. It will be Anastasia Polikovska she is a student in the Lviv Polytechnic National University. And Anastasia, are you hear me? Anastasia?
Yes, good day. I will try to share my
Okay, good
screen.
afternoon. Yeah. Yes, we are waiting for.
And can you see it? I will close it.
Not yet. Now, yes. Now, yes, we can see.
Maybe I will.
You should go into the full screen mode because
it's not
not.
seen. Yes, I will turn it on. Now you can see. I hope you don't see like participants. I will make it smaller. So today we're gonna talk about the diversity of Malva genus plant extract mediated synthesized nanoparticles. The Malva genus plants belonging to the Malvaceae family and found in Ukraine and all or a temperate region in Europe has been traditionally used in medicine, but it is limited. So here I will talk about some modern like technique of using it. This plant contains many phenolic compounds and flavonoids that are key to a sustainable green synthesis of nanoparticles with unique properties. In this slide, you can see the aim of my work is to explore the diversity of nanoparticles using extracts from plant of the Malva genus. Sorry. It's okay.
Sorry, but I have to a little bit interrupt you because we just see your first slide. Maybe
first
you
slide.
Yes, maybe your
problem with. Oh.
Try again, share with us your screen and try again.
And now
we can see, but try to.
Third slide you saw, and fourth.
Yes, just first.
It's changed, yes.
Not just first slide all time.
Oh, this. So, it's just some problem. We don't often use Zoom. Maybe demonstration will share. You can see a first slide.
Now we can see that possible this is the second slide. Yeah, perfect. Okay, continue, please. Yeah. Now it's okay. Everything is
Okay.
going all right. So please, you start your presentation again, maybe. Okay.
Today we're going to talk about the diversity of Malva genus, a plant extract mediated synthesized nanoparticles. So in this study, I discovered some like relevant articles in the past 5 years about nanoparticles that was synthesized based on extract of Malva plant. So first, it was antibacterial and antifungal activities of these particles. Can you see it? I hope so.
Everything good? Yeah.
Okay, thank you. Antibiotic resistance is one of the major problems, and some resistant bacteria and fungi can be killed by some traditional antibiotics. On the other hand, nanoparticles, they use another mechanisms that antibiotics to kill bacteria. For example, as though TO2 nanoparticles synthesized using Malva porphyrola extract exhibit antioxidant, antibacterial, and antifungal activity against Staphylococcus pyogenes, that are most known as Staphylococcus species, Salmonella typhium, and Candida albicans. These particles using photocalyptic mechanisms that kill bacteria with forming under sun radiation ROS, reactive oxygen species. In that case, they are good for the cells, these reactive oxygen species. Also a good gold and silver nanoparticles obtained in reaction with Malva versicolata extract had demonstrated antibacterial and purification properties. Silver nanoparticles can work against fishes pathogens, and it can also purify the water. It's about golden nanoparticles by shift bases that can be used for industrial dyes, pigments, agrochemical, and pharmaceuticals wastewater. Nanoemulsion that was based off Malva porphyrola extract also possessed antibacterial and anti-diabetic properties. This nanoparticle has a high activity against pathogenic fungi such as Fusarium or Penicillium or Aspergillus. The extract of its nanoformulation also show antibacterial, anti-diabetic properties that was tested on rats. Here you can see also links to these articles. And the other is cytotoxic activity. Cancer was one of the most significant public disease globally, and second leading cause of death. The advantage of nanoparticles is target delivery, and it has high efficiency right now. Silver nanoparticles that was prepared from Malva sylvestris extract has shown cytotoxic effect toward human renal carcinoma cells and kidney carcinoma and human embryonic kidney cells. They used sampled cells, like cell lines. The nanoparticles could resist significantly against those cells in a time and concentration-dependent manner. And quantum dots that was obtained by mediated synthesis with Malva sylvestris roots extract exhibited any cytotoxic effect on human prostate epithelial cells that they see that, but it can utilize the fluorescence of cells. And it can be used for imagining human prostate epithelial cells. Another is water purification activity. It's important because only 0.3% of our water are available for 8 billion of population. So nanoparticles is a suitable candidate for various water treatment techniques. High surface area, high chemical activity, and better antimicrobial activity make this material efficient for water remediation process. Nowadays, it's more environmentally safe. So copper nanoparticles that was made with Malva sylvestris extract has ability to remove methylene blue from water solution. I will say it's methylene blue was used like a control that it can like reduce its power. So in other studies with silver nanoparticles synthesized with Malva porphylova extract, they show that these nanoparticles can reduce not only methylene blue but atrazine that are herbicides that are cancerous. So it's important to make new nanoparticles in green phase too, to remediate our water or use it in anti-cancer target disease control and for antibacterial properties that will help us, for example, in some, for example, antibacterial furniture in our hospital and so on. This review shows potential of use nanoparticles synthesized with plant that distributed in Ukraine for its antibacterial, antifungal, antidiabetic, cytotoxic, and water remediation activity and other possible application. Here you can see sources that I used in my study. Thank you for your attention, and I open to your questions.
Thank you very much for your interesting report. And please, someone have a question maybe?
Sorry?
It seems we don't have any question at this time.
Oh.
So everything is. Oh, we have. Yes, we have.
Thank you for your presentation. I will ask about the destruction of methylene blue. What was the decomposition degree of such dyes? What concentration?
It wasn't my study, but they used like a solution of methylene blue, and that's all. It was study of Iraqi scientist.
Thank you.
Thank you.
Thank you very much. Maybe if we have additional question, it will be maybe in our chat because we need in saving the time. Yeah. So thank you a lot again for your presentation, and we should go into our next presenter. It will be Professor Sergei Shulha. From the Institute of Food Biotechnology and Genomics of the NAS of Ukraine.
Yeah, it's
good afternoon.
Hello, good afternoon.
Please,
but my presentation in your organized committee.
Okay, yes, it's already on our desk, and you can just a moment, appointments, yeah.
In any case, if it's possible that I disappear from the monitor because we have the problem with internet, so a lot of sorry.
Okay, and we can
nevertheless,
see
yeah, I see. Nevertheless, thank you very much for the possibility to to show our work and invitation for this conference. My presentation was connect with Alzheimer disease. No. It's maybe back. Yeah. And research was supported by the National Research Foundation of Ukraine. Grant number, you see, next, please. We talk about the Alzheimer disease. Why? Because Alzheimer disease, or the short form AD, is a well-established neurodegenerative disorder characterized by the memory impairment, cognitive dysfunction, and behavior of disturbance. In any case, we think that maybe the first step for the of the appearance of Alzheimer's disease, or AD, it was the inflammation, maybe the earliest sign of AD. In this case, we tried to find, first of all, the drug, or so-called active pharmaceutical ingredient, which can protect the neurodegenerative disease, and the drug delivery system, how it is possible to, put all API target form. Next, please. This is the short introduction for the AD. We talk about the two methods of AD, or two, proposition for the appearance of AD. Unfortunately, causes of AD are currently unclear, but nevertheless, by experimental results, we receive some results as organized beta amyloid plaque in the neuron, and the same situation with the tau peptide, which when you see the microtube destroyed with the hyperphosphorylation. When according to the beta amyloid peptide, we have the amyloid precursor peptide, which cut by beta, gamma, alpha, and we receive the beta amyloid monomers, then form the beta amyloid oligomer, profibril and fibril, and then beta amyloid plaque. Next, please. We try to investigate the liposome as a drug delivery system, and we work with liposome, a short form for the chemical structure of the phospholipids. We have the hydrophobic tolls and hydrophilic head. As usually, hydrophilic head sweeter ionic, plus, minus, and cationic or anionic form. Nevertheless, the fatty acid tolls is as usually saturated and unsaturated fatty acid. Next, please. As usually, the phospholipids aggregation in water. So this calls, we have the, emulsion, water in oil, or oil in water. We have now the, situation with oil in water. As usually, the aggregation in water, phospholipids organize the planar, the upper and down, you see water core, and below with phospholipids. But according to the low minima of energy, this planar organized in the ball. You see, including first of all interior the water core, and outside the water. Next, please. This is the main critical stage of liposome preparation, production, and control. You see, the main situation is the lipid substance. It's very, you see, interesting, and in future, it's you see the main substance content. It's raw material for the liposome. It's interesting question. Next situation, the obtaining of liposome. This is the method, and some parameters. You see the temperature, maybe pressure, maybe quality signs. Then another, the sterilization or filtration, because it's necessary to receive the liposome as a sterile situation. We work with two methods. Next, please. We use the raw material for the liposomes as phospholipids from the sunflower lecithin. Sunflower lecithin, you can see the all parameters which we receive from the dried oil lecithin, and phospholipids consist approximately 98.35. This is really the good quantity for the phospholipids. Next, please. As usually, phospholipids for the lecithin, when we received, we determined, you see, the component of the phospholipids. First of all, this is phosphatidylcholine, approximately 60%. Then phosphatidylethanolamine, approximately 20-25%. And phosphatidylinositol, approximately 5-7%. Maybe the fatty acid, and next, these are form of such ingredient. It's very interesting that in these phospholipids, you see some, we detect the chlorogenic acid. Maybe in future, it will be the main situation for the stability of liposomes from the sunflower. We determined the liposome stability by EPR. First of all, we use the spin probe nitrogen radicals. As usually, you can see this the base adamantane and other. Next, please. And we determine the temperature depends of correlation time of rotation diffusion, because as usually you can understand that long time, great rigidity, and great stability. You can see that the dot of the liposome from the sunflower seed is the upper, and on the left and on the right. Next, please. Next, we try to determine the initiated exudation. Initiation exudation with azoinator. Azo bis methylpropionate dehydro my goodness, chloride, yeah. In any case, it's possible that signal intensity, next please. Thank you. Signal intensity of the encapsulation of B radical of liposomes, it's possible to determine the stability of liposome from the rather raw material. You can see that stability from the sunflower lecithin, it's really more stable according to the other liposomes. Next, please. And the visualization. We use curcumin excitation and emission. We use the microRNA with the some label, fluorescent label with Psi5. And it's possible to, you can see it on the left-hand picture, this is the combine. You see the green color. This is the penetrate curcumin in the bilayer, and in the water core microRNA with Psi5. Next, please. And visualization of curcumin and microRNA in liposome, we use the you see the representative, you see visualization of single optical with confocal microscope, and it's possible they show the X-plane cross-section and the fluorescence model. And the same, it's possible to determine you see, distribution of curcumin and microRNA. When we use the microRNA, because microRNA is usually connect with the translation and you see, determine the behavior of the gene. In any case, it was shown the curcumin is intercalate into the lipid bilayer and microRNA into the aqueous care of liposome. Next, please. Yeah. And this is, you see the results as we received after the model of Alzheimer's disease. Alzheimer's disease, we prepare with the injection of beta amyloid peptide 45 injection direct to hippocampus. And it's possible that after 5, 10, 20, 15, and 30 days, it's possible that effective duration, of course, use on aerosol of the liposome from the complex containing curcumin and microRNA with special, you see, concentration. And for the model of the Alzheimer's disease should be at last 15 days. More than 50 days, we have the really good results. Next, please. And this is the efficiently to use the spray of curcumin and microRNA in liposome form, spray to the nose, and it's possible to look, if you look on the interleukin-6 and beta amyloid 40, you can see how change the concentration after 10 days AD and AD plus therapy. You see more than 70 up to the 70% down. Next, please. And this is the summary, short summary. This phospholipid liposome showing the more stable initial oxidation and temperature than soybean and egg for yolk phospholipid liposomes. They obtained data from the sunflower phospholipid using its raw material for the nanoscience containing creation liposome for the active pharmaceutical ingredients transport and strategic for the Alzheimer's disease treatment, taking into account the key role of the liposome form of flavonoid and microRNA. And 15-day therapy, you can understand the results is really not bad. Next, please. This is our colleague who worked hard in this work. And next, please. Thank you very much for your attention. Exactly. Yeah.
Yes, we appreciate you for your important research and explanation. And I would like to ask our conference hall about question. If you have question, yes.
If it's possible from Zoom question.
Thank you. Thank you for your presentation. And my question is about do you use mean and contrast again, or as a therapy or as a contrast?
Unfortunately, it's not so good sound. Can you repeat once more because it's not so good sound?
Okay. Do you use curcumin in your study as a contrast against or as a therapeutic again for the therapy or as a contrast to visualization?
No, it's according to the therapy.
Thank you. Thank you.
Thank you very much. Maybe one more question.
If it's possible
we
from
have
Zoom.
Yes, one more, please. Please, Oksana.
Okay. For me, it's quite similar question. I would like to know the role of curcumin than your drug delivery system liposome, and probably you would like to have some synergetic effect between curcumin and RNA.
Well, thank you. First of all, we use curcumin that in previously our work, we determined that curcumin can block, you see the cutting APP with gamma and beta secretase and block the site of cutting. This is the main idea why we use curcumin. And according to the, you see RNA, it's possible to block the translation of APP and beta amyloid peptide.
Did you try or do you have idea to use the same system as anti-cancer therapy?
It's a tricky question because we work hard, especially for the Alzheimer's disease. And maybe in nearest future, we'll not connect with the tumor. Our plan not connect with the tumor. Maybe, because as usually a lot of research work with not only curcumin, with quercetin, rutin, squalene, and other. You see flavonoid and prepare some liposome and another form drug delivery system to use anti-cancer therapy.
And probably one just remark, do you, or even question, are you sure that you have only liposome and you not formate also some kind of micelles?
Well, you see, first of all, we use you see, as usually, electronic microscope when we, first of all, prepare you see the emulsion of liposome. And then we can determine how we you see inject the emulsion into the nose, because it's well known that in some part of the nose port we have no BBB, blood-brain barrier.
Thank you very much for your very interesting talk.
Thank you.
Thank you very much also for your important talk and your answers. And we move forward to our next speaker. It will be Dr. Rostislav Vazhnenko from the Taras Shevchenko National University of Kyiv. Yes. Rostislav, sorry.
Good afternoon.
Yeah, good afternoon.
Can you hear me? Can you see me? Yeah.
Yes, we can hear you, but not yet you're sharing with us your presentation. Yeah, we can
Okay,
see.
right now I will
Yeah.
start sharing.
Mhm.
Yes.
Yeah. Yeah.
Can you see my screen now?
Oh, yes. Now, yes.
Oh, very
Yes,
nice.
yes. Yeah, please.
So I will start. Good afternoon. I'm glad to have the opportunity to tell my report. The name of my report is Production of TB2-based layered ceramic composites with weak carbon interlayers by mean of reactive hot pressing. Due to the rapid development of penetrator projectiles, there is an urgent need to improve body armor plates. Since the old armor plates made of metals, for example, steel or titanium alloys, are no longer effective. As a solution, it has been proposed to manufacture armor plates from ceramic materials such as boron carbide, titanium diboride, and silicon carbide, which are mechanically stronger. This is explained by the difference in chemical bonding between metals and ceramics. Metals are characterized by metal bonding, while ceramic exhibit predominantly covalent bonding. Owing to covalent bonding, ceramics may demonstrate significantly higher hardness and strength compared to metals. However, a significant drawback of ceramics is their brittle fracture mechanism. This fact results in the low durability of ceramic armor plates, meaning that after one or several projectile impacts, the armor may become completely fractured and unsuitable for further use. To overcome this problem, we propose the use of layered ceramic armor plates, in which one layer has high hardness, while the other is less hardness, and contains a large fraction of softer faces. The problem of low durability can be resolved since, according to Griffith's theory, a crack tends to propagate through a medium with lower surface energy rather than through one with higher surface energy. After passing a layer that in the softer one, after passing through several pairs of layers, the crack will stop at the interface between the hard and soft layers, as it will not retain enough energy to pass through another soft layer. Instead, the crack will begin to propagate within the hard layer. As a result, after the projectile impact, only a portion of the layers will be destroyed, while the remaining part of the armor plate will remain intact and capable of withstanding additional impacts. It's also important to know that the height hardness of the hard layers in our best samples is around 38.5 gigapascals by Vickers hardness, significantly hinders the penetration of projectiles with lower hardness, which has been confirmed by experimental studies. Thus, the problem of low durability of ceramic armor plates can be considered solved. In our study, we experimented with different composition. For the hard layer, it were boron carbide, titanium diboride, silicon carbide, and for the soft layer, titanium diboride, titanium carbide, graphite. An important criterion for selecting the hard-soft phase pair was the closeness of their thermal expansion coefficients, in order to prevent the formation of residual internal stresses, which could make the material unstable under external loads. All powders were milled to particle size on the order of submicrons, with occasional agglomerates 5 to 10 microns. We employed the technique of reactive hot pressing. The reactive sintering allows optimization of energy consumption during ceramic fabrication, and very importantly, enables the in situ formation of graphite during the chemical reaction. This was essential since all attempts to fabricate samples with soft graphite containing layers by direct addition failed. The sample just delaminated. The best properties were demonstrated by samples with the following hard-soft phase pair. You can see it on my presentation. For hard layer, it were 4B4C plus 2TC0.8. And after reaction, it were 2 titanium diboride plus 2.6 graphite plus 3 B4C. For soft layer, it were B4C plus 6 TC0.8, and after chemical reaction, it were 2 titanium diboride plus 2.6 graphite plus 4 titanium carbide. And if you can see in my photos, we saw layers of this material. To make the samples, we should reach 1900 degrees, and we should stop heating process and hold this temperature for 4 minutes. As we can see, two waves ocean gauge at 1600 degrees and 1900 degrees. Here is a result of electron microscopy of our material, and we can see that material is really layered. Now I will go to results of measuring. There is a hard phase hardness that's 38.5 gigapascals. For soft phase is 13.7 gigapascals. Now about fracture toughness for hard phase is 4.1 megapascals by square meter, and for soft phase it's 5.5 megapascals by square meter. And as a result, the theory of crack arrest at the hard-soft interface was experimentally confirmed. As you can see in my picture, can you see my mouse? Yes? Okay. As you see my mouse?
Yes.
The crack start growing in this way, but crack will face the soft phase, and it not going down. It will propagate in hard layer. In this photo, we cannot see difference between hard and soft layer because by optic microscopy, we can't see this difference. We can see this only in electronic microscopy. It also be noted that the samples with this phase pair exhibited enormously low density. Theoretical density is 3.6 gram per cubic centimeter, but our experimental values of density is 2.4 to 2.8 gram per cubic centimeter. We cannot yet explain this effect. We have only theories and hypotheses, but it further enhances the efficiency of our material as armor. Since the reduced density makes the plates lighter, which significantly improves the particle usability. The work was supported by the National Research Foundation of Ukraine. Grant, you can see in my presentation. And thank you for your attention. I'm ready to questions.
Thank you very much for your contribution, first of all. And do we have any questions from the conference call? It seems everything clear. Thank you again for your report. And we're going to it. And the next our speaker will be PhD student Polina Zaremba from Zabolotny Institute of Microbiology and Virology of the NAS of Ukraine.
Good afternoon.
Yeah, good afternoon.
Just a second, I will share my screen.
Yes, please. Yes, we can see your screen, but would you time to okay? Yes, everything going good. And please, you can start.
All right, thank you. I would like to present our study about biocompatible polyhydroxylated fullerenes that demonstrate complex anti-influenza activity. So we are all familiar with influenza viruses that cause seasonal colds, as well as the most famous their representatives is influenza A virus that has caused quite a few pandemics in the last century. So the influenza viruses, as RNA-containing ones, they quickly mutate, and that helps them to combat our immune responses as well as to acquire resistance to antivirals. And antiviral drugs are especially necessary for vulnerable categories of the population, such as children, elderly, pregnant women, as well as immunocompromised individuals. Currently, neuraminidase inhibitors are the only globally widespread type of anti-influenza drugs, and their use increases the frequency of mutation responsible for the resistance. Even though the frequency is luckily not as high as it could have been, we still need to have it in mind and keep searching for the safe drugs, um, especially in the picture of the last not so in the last recent SARS-CoV-2 pandemics, where antivirals could have been the first line of defense in the virus spread. So the search remains, and scientists have been paying a lot more attention to nanomaterials for the last few decades. As representatives of the nanostructures, fullerenes are unique structures that attract attention of many specialists in different fields because of their chemical and physical properties. Fullerene derivatives have quite a special place in antiviral research because we have a number of studies devoted to them, and we can see their effect on different types of viruses, both DNA and RNA viruses. But the main problem of using fullerenes in biology and medicine is their low solubility in water. However, one of the solutions to this problem is hydroxylation. Hydroxylated fullerenes or fullerenols are another full branch of the fullerene derivatives field in virology and biology in general, and they have been proven to be relatively low toxic and quite biocompatible, which makes them attractive candidates for the role of antiviral agents. So the goal of our work was to study the toxicity and antiviral effect of the mixture of polyhydrated fullerenes on influenza A virus. All of the experiments with the virus were conducted using the model cell culture MDCK, and they were performed in different schemes that will be explained later during the presentation. The evaluation of toxicity required a few cell cultures. We used cultures of different origin as well as cancerous ones and bulb C mice. The tested compound itself, or the mixture of fullerenes, was with the mixture was performed high-performance liquid chromatography to identify the contents, and it was determined that the majority of the fullerenes in the mixture are classical C60 and C70, and their total percentage of the content was more than 86%, and the rest were the higher ones from the C76 to C86. As for the toxicity, according to the results of the MTT-assay, which allows us to assess cell viability, we found that fullerenols were the least toxic to the MDCK cells, which are normal dog kidney cells, And the most toxic effect they showed for the cancerous cell lines, such as human lung adenocarcinoma and monkey B lymphocytes that also are Epstein-Barr virus positive. In vivo or using mice, we have conducted an experiment where we used a few groups of animals that have received a dosage of different concentration of the fluoronols orally. And then we observed their behavior up to 21 days. So, as a result, the mice in all experimental groups were alive and behaved totally normal during the whole observation time. Also, we have performed the hematological analysis of their blood samples after day 3 and day 21. So the parameters of the blood parameters of groups that have taken a drug were similar to such of the control that only had water, and we had the minor exception of the changes in the level of hemoglobin and platelets. As for the antiviral activity, the first scheme that we used was to determine the effect on the adsorption. For that, fullerenes were introduced to the cell culture simultaneously with the virus in order to see in the stage when virus should adsorb on the cell surface in order to start the infection. So we have got a quite strong influence of the fullerenes on the virus adsorption, and the inhibition of reproduction was overall about 80% for the majority of concentrations. Then after that, we also identified the infectious titer of the newly synthesized virus or virus progeny, and found out that in the same concentration range, or for the majority of concentration, the decrease of the infectious titer was more than 50%, even leading up to 100%. So the results clearly indicate the influence of fullerenols on the process of adsorption as well as on the infectivity of the virus progeny. The next scheme was about introducing the fullerenols in already infected cells immediately after the infection, then after 4 hours and after 24 hours. As you can see, we have got quite similar results for the immediately after and 4 hours after infection, because for the majority of the concentrations, except for the lowest one, the inhibition of the viral reproduction was higher than 80%, again leading up to 100%. And even after 24 hours in the beginning of infection, virus was strongly inhibited with the rate of more than 70%. Similarly to the previous scheme, we also observed a decrease in the infectious titer of the new progeny, and with the full inhibition of viruses at concentration range from 0.5 to 1.4 milligrams per milliliter. The last scheme, virucidal activity, involved in pre-incubation of the fullerenols with the virus before introducing them into the cell culture. So we wanted to see the impact of fullerenols on variants outside the cells. And the highest concentrations from 0.5 to 2 milligrams per milliliter completely inactivated variants to the point that we did not observe any cytopathological effects on the cells. and the lowest concentrations weren't as effective, but still was effective because they decreased infectious titer up to 2 to 3 orders of magnitude, which is quite sufficient. Considering all of that effect that we have observed, we had some theories on mechanisms of action and how can fullerenes interact with influenza virus. So virus it is an enveloped virus and it has a liquid membrane, lipid bilayer or membrane outside the virion. And the first thing that fullerenol will be interact to is the membrane. So with the help of the molecular dynamic simulation, we found out that actually fullerenol C60 interacts with the lipid bilayer of the influenza virus through hydrogen bond formation, and this interaction leads to the membrane distortion, and which in turn can affect the surface tension and the membrane fluidity. The latter can affect the functioning of the transmembrane proteins, such as hemagglutinin and neuraminidase, which are essential for the successful infection in the cells. Considering that we observed the effect not only for the extracellular virus, but also the intracellular one, we hypothesized that another mechanism of action can be the interaction of the fullerenes with the polymerase, with the viral polymerase. And indeed, we found out that fullerenol C60 also interacts with the pocket of the polymerase interaction with the RNA primer. This exact interaction also is relative to the fact that a lot of fullerene derivatives that I have previously mentioned and their effect on the different RNA viruses also is connected to their interaction with viral enzymes. Therefore, the studied polyhydroxylated fullerenes not only being effective on against influenza virus, as well as being promisingly biocompatible, they are quite promising anti-influenza agents, and they could be used for virus spread prevention schemes and in future strategies of fullerene-based drug design. Thank you for your attention.
Thank you very much, Polina, for sharing with us your important results. And I would like to ask also our friends Paul and Sue about some questions. It seems we have a question at the moment. So thank you again for your presentation. And we are moving forward. And our next speaker will be Dr. Alina Litvinenko from Bogomolets Institute of Physiology of the NAS of Ukraine. Alina.
Good afternoon.
Good afternoon. Good afternoon.
Wait a minute.
Yes. Yes, we can see your presentation, and you can start.
Okay. Greeting to all participants, and organizers of the conference. Thank you for your opportunity to speak and present our research. Our work called the effects of silver nanoparticles on small intestine cell and cell of the follicular environment of oocyte in female mice. Study were carried out in Bogomolets Institute of Physiology in Ukraine. In last decade, the use of metal nanoparticles, in particular nanoparticles, has become extremely widespread in the medical, food, and pharmaceutical industries. A number of preparations with antibacterial, antiviral, and antifungal properties have been created based on colloidal silver. However, the effect of silver nanoparticles on the intestine and reproductive system have not been sufficiently studied. Regular cell death plays an important role in development, tissue homeostasis, inflammation, immunity, and many pathophysiological conditions. And it can arise from disturbances in the intracellular or extracellular microenvironment, in particular due to the influence of reactive oxygen species and DNA damage. Today, research into regular cell death is relevant as one of the possible new therapeutic strategies for prevention functional disorders of both the intestine and premature ovarian failure. So the aim of the work was to evaluate the effects of silver nanoparticles on small intestine cell and cell of the follicular environment of oocyte under condition of experimental premature ovarian failure and the use of resveratrol in female mice. First of all, we would like to express our gratitude to the cooperation and provision of silver nanoparticles in polymer matrix to researchers from Taras Shevchenko National University, namely Natalia Kutsevol and Yulia Kuziv. Synthesis of silver nanoparticles has been performed using partially hydrolyzed star-shaped grafts copolymer of polyacrylamide to dextran auxiliary capping agent. The star-branched copolymer proved to be a very good template for nanoparticle synthesis due to high local concentration of functional groups. Detail of synthesis, identification, analysis of silver nanoparticles are described by Kutsevol and other research in the Journal of Structural Chemistry in 2015. Formation of silver nanoparticles was confirmed with transmission electron microscopy. Exemplary team images of silver nanoparticles synthesized in the presence of the ioniotic copolymer at pH 7 are present in figures 1a-b. The image shows that the obtained colloids contain mainly single silver nanoparticles with a small portion of nanoparticles clusters. Single silver nanoparticles are both sharp-shaped and polyhedron-shaped. The nanoparticles are sized from 10 to 16 nanometers. Experiments were carried out using white laboratory female mice of the albino line, according to Geneva Convention, and have been proved by the Biomedical Ethnic Committee of Bogomolets Institute. Research group, first control group, next experimental premature ovarian failure. This model was created by the immunization with kidney antigen suspension obtained from the mother. Immunization was carried out 4 times, once a day, intraperitoneally at the rate of 2 microliter suspension per 10 gram of mouse weight, according to the scheme. On the first 3rd, 5th, and 26th day, 4 weeks after from the beginning of the experiments. The third group is the group animals with experimental premature ovarian failure and treatment with silver nanoparticles, and fourth group with experimental premature ovarian failure and treatment with silver nanoparticle and resveratrol. Isolation of a small intestine cell enterocytes was carried out according to Kimura, by which a suspension of epithelial cells was obtained from an upper part of the ileum villus. They determined the parameter were viability and the separate way of enterocytes and the cell of the follicular environment of oocytes. Sampling of experimental material from female mice was carried out under anesthesia the day after the last administration of silver nanoparticles. The apoptotic and necrotic death of enterocytes and follicular environment of oocyte cells was estimated by morphological characteristics using in vivo methods of two-color fluorescent nuclei acid dioxide and propidium iodide. Cells standing in this way can then be counted with apoptotic nuclei displaying characteristic hypercontaxation and fragmentation into distinct globules. In contrast, necrotic cell display as well an deconcept morphology that is very distinct from features exhibited by apoptotic nuclei. For the statistical analysis of the results, the software package of graph patch prism have been used. Okay, so we obtain the following results. This slide shows change in the vital activity of enterocyte in the ileum under the experimental condition studied. Under experimental premature ovarian failure condition, second column, there is decrease in the number of live cells and increase in the number of such cells with morphological signs of apoptosis and necrosis. The introduction of silver nanoparticles under experimental premature ovarian failure condition had no toxic effect. No statistically significant change in number of live, necrotic, and apoptotic cells were detected. Under the experimental premature ovarian failure condition, the use of resveratrol and silver nanoparticles causes an increase in the size of live cells, enterocytes, and decrease in apoptotic cells. And no significant change in cells with signs of necrotic were detected. So new data on the effects of silver nanoparticles on small intestinal cells have been obtained, encouraging further research, possibly therapeutic treatment of such nanoparticles. In our investigation, the experimental premature ovarian failure caused change in viability in follicular environment cells. There was a decrease in number living cells and increase the number of cells with morphological signs of apoptosis and necrosis. We have shown for the first time that the introduction of silver nanoparticles under experimental model of premature ovarian failure condition leads to a suppression of the viability of this cell. Specifically, the proportion of live cells decreases and cells with morphological signs of apoptosis and necrosis grow compared with the other group. It was established for the first time that under experimental premature ovarian failure condition, the use of resveratrol and silver nanoparticles cause growth in the number of live follicular environment of oocyte cells and reduce in the proportion of cells with apoptosis and necrosis morphological signs. Our data indicate that resveratrol has a positive effect on folliculogenesis in the setting of experimental premature ovarian failure at the initiation stage of chronic kidney disease. Further research are needed to clarify the mechanism of action of silver nanoparticles and resveratrol as a therapeutic agent for influencing ovarian cells and oocytes in the setting of experimental premature ovarian failure. Special attention should also be paid to the interaction of copolymers nanoparticles with the immune system intestines, as this is likely to determine center non-specific immune responses. Further research is needed, possibly initially in vitro, to help improve our understanding of the process that occur when silver nanoparticle and resveratrol interact directly with cell. The conclusion presented on the slide were voiced and discussed during the report, so please do not read them out loud. And we would like to thank Natalia Kutsevol and Yulia Kuziv for providing samples of copolymer silver nanoparticles for the study, and thank you for your attention.
Thank you very much for your very important and interesting talk. And also, I would like to ask about question. Maybe in Zoom, no, but maybe I have questions. Yes. Now you can hear me. What's the potential long-term reproductive health implications result from the observed effects of silver nanocomposites on oocyte-related cells? Long-term, reproductive.
In our investigation, silver nanoparticles have influence on a reproductive system and influence on folliculogenesis. Follicular environment oocyte cells is very important cells for folliculogenesis and its viability can understand the quality of oocytes. That's why silver nanoparticles investigation, their influence is very relevant now.
So, okay, thank you very much for your answer and for your contribution in our conference. And now we are going to the end of our session because unfortunately our last speaker, PhD student Maxim Ankolov, has not any opportunity to contribute to work of our conference in this moment. And we have now reached the end of our session. Thank you to all our speakers for their excellent presentations, and to everyone for contribution and participation. The conference sessions will be continued tomorrow morning at 9 a.m. Kyiv time, and we invite you all to join us. We wish you a pleasant evening. See you tomorrow.